thank you everyone. Very warm welcome to this session. So today I'll be talking about a very important and interesting element of decarbonization. So we've been talking quite a bit on electrical utilities and how the electricity system could be made decarbonized. But one of the key elements of complete decarbonization and 100% RE is also to look at heating systems. So my focus in today's lecture is on the high temperature heat pump systems, primarily focusing on industrial heating. My name is Professor Satyanarayan Seshadri. I'm from the Department of Applied Mechanics at IIT Madras. I run a lab called as the Energy and Emissions Lab, primarily focused on decarbonizing industrial process heat. So let's get started with what do we really mean by energy. Primarily, there are two modes of utilization, electricity and heating. You're quite familiar with most of the electricity-based modes, and all of energy efficiency is targeted towards that, where you look at lighting, LEDs, cooling, high-efficiency cooling, compressors, look at screw compressors, VRV, VRF. Water is a really big deal. Water energy nexus is well known, and improving mechanical work output that is driven through electricity. The other big element, which is heating, here there are four key elements, and here we are not talking about power generation from steam. We are primarily talking about industrial process heating. So of these four elements, all four are poorly decarbonized across the world. That's because they have been run through very simple systems like natural gas, coal, biomass-based systems, and furnace and burners, depending on the temperature need, it is one of the difficult sectors also to decarbonize. So in this lecture, I'll be talking primarily about steam and hot water system. So what are we trying to do? Generally, our approach has been to reduce, make burners, boilers, everything more efficient, reuse as much as possible, reuse the energy generated at multiple levels. So the CHP systems, which is combined heat and power and all of that come here. Recycle primarily to see if there is way to upgrade the energy, waste heat recovery, technologies like organic Rankine cycle and all come here. And it's been quite successfully used, but again, the economics has been a big stumbling block. And replace is what we'll be talking today. Is there a way to replace my heating systems with something better, something that makes it easy to decarbonize? So the question that we want to ask is, how do we achieve 100% RE when bulk of industrial energy need is for heating? So this is true across sector, especially in a large manufacturing setup like India, where food, the fast-moving consumer goods is one of the biggest manufacturing element, and their heating nearly constitutes about 40 to 50% of the energy need. So the simple answer is fire your boiler. So if you fire your boiler and make everything through electricity, then you can easily decarbonize. So we will figure out, are there ways to fire your boiler? So in this lecture, we'll talk a little bit about some economics and case study. But first question is, why are boilers bad? And it is the nature of that beast. As you all know, in most combustion system, there is an exhaust, and the exhaust contains a lot of energy. And many times we have seen our thermodynamics 101 that we really want to utilize energy at the highest temperature possible. But most of the process heating system that we talked about, for the sectors we talked about, you don't need that kind of heat. You need something very benign at 100, 120 degrees C, but you still burn boilers with coal or natural gas, which the combustion temperature is near 1000 degrees C. So essentially you are throwing away all the heat. That's what people call as boiler efficiency. There is a lot of effort to improve that efficiency, but it's still a lot of heat is thrown away. And the emission is another major factor. We generally miss out on the problems from emission from small boilers. People talk a lot about Delhi in this winter. Crop burning and vehicles are talked a lot. But Delhi has about 7,000 plus small boilers in and around the capital territory, which is uncontrolled, meaning there is emission regulations do not apply to small boilers, and that kind of contributes to this kind of an emission. And all those small boilers are used for very low temperatures. So there is really a good need for decarbonization. So what do we use? So why do industries need this kind of heating? Some examples of industries that need low temperatures and the processes that I've listed here, such as pre-treatment, cooking, cleaning, boiler feed water, degreasing. So a lot of fabricated items need cleaning, and a majority of low temperature heat is for cleaning applications, including in dairy and many other sectors. And it is almost, except a few sectors, this requirement is kind of across the board. And these are some examples of the top 3 low temperature energy consuming sectors. So when I say low temperature, I'm generally talking about less than 400 C, and out of which a significant portion is less than 100 degrees C. Now you can see here textiles, maximum is about 100 degrees C. Electroplating, which is all your shiny polish that's on any metal that's for corrosion prevention or aesthetics, less than 100 degrees C. Automobile industry, a lot of sheet metal and metal processing less than 100 degrees C. And all of this is less than 50%, less than 400, and a majority less than 100 degrees C. Now, what is the actual potential of this heat? I have just picked up the top 5 sectors. This is a study done for solar heat in industrial process. But I believe solar heat is a very poor substitute because it's infirm, it requires a lot of infrastructure and storage. And that's the same sector we will be addressing with a technology that we're going to describe called heat pumps. Here again, you can see a theoretical potential as of now based on the installed base is close to about 28 gigawatt hour thermal. And the economic potential, which talks about as of today, without any policy, any kind of intervention, it's sustainable, at least about half of it. And this alone contributes to more than 40,000 crores rupees in terms of the size of the market and a significant potential to be tapped. Why is this important? We all know the price of diesel. A lot of these small heating requirements are supported by fossil fuel. A few of them are supported by biomass, but most of them are by diesel, kerosene, or natural gas kind of a requirement, natural gas kind of a system. So it really helps us because the price of diesel or any fuel is not going to come down, and electricity is quite stable. And this is the interesting trend. I mean, electricity prices have really dropped, and it's likely to remain stable, whereas fuel prices are going to continue to rise. So how do we tap in? The trend is electrification. Yesterday we talked about electrification of transport. Professor Ashok talked about electrification of agriculture, of construction, but electrification of process heating is also a major thing that's going on across the world. A lot of places, this is getting the status of renewable credits. So there's also another important trend where people are looking at, where when you have a high penetration scenario of renewables, now what does that mean? It does mean that substituting with your existing fuels with something else require ability to generate heat and store heat. When I say heat, it can also be in the form of thermal energy for cooling. We briefly talked about cooling loads yesterday, but storing heating is also one of the major elements, which along with the other kinds of storage that you looked at is going to really drive this transformation. So how are we going to do that? We are primarily going to do that with a technology called as high temperature heat pumps. High temperature heat pumps are not something that you don't know. You know it quite well because we all use heat pumps by the way of refrigerators and air conditioners. Here, what we are really doing is playing with the thermodynamics, playing with the refrigerants, working fluids, and robustization of technology to be able to deliver the requirements we have. So currently, commercially available are things that we can develop and deliver hot water and thermic oil at temperatures less than 100 degrees C. Steam is something that is emerging. A lot of people are working on it across the world, but it is still in the pre-commercial state. We are also working on that. We'll talk about it a little later. So as we know, if you want to compare the cost of heating, the choice is fairly clear. You can imagine this is maybe a year and a half old. Now it has become even worse. Electricity has remained the same, but diesel, kerosene, LPG, HFO, all these fossil-based fuels have already become quite expensive. And you already knew here, electricity was already a better choice compared to diesel for heating. And now with heat pumps, it becomes an even better choice. And given the trend of long-term price of stability of electricity, I think it makes more and more sense for us to look at alternative methods for heating. And just to give you a perspective, the size of the market in India that is currently available, the total available market size installed base is about 42,000 crore rupees. Based on a very benign price of heat pump that we took here. So it's a large opportunity, but the size of the market does not mean that the market is fully done. Across the world, it is still an emerging technology. That's why I think all of us as researchers need to do a lot more case studies and demonstrate. At the heart of it, what is the system? There are simply 4 key components. The compressor, what you have here, the heat exchangers, which is all mechanical systems, and the evaporator, and the heart of it is the controller. So technology wise, it's something that worldwide people understand very well. There is enough manpower and skill power to deploy and test and service it. It is really about the awareness, really about doing some case studies and taking it to the market. Here is one example. Here is a project that we did for a leading auto component manufacturer here Chennai, who was using SKO, which is the superior kerosene oil, which is similar to the aircraft grade oil, for heating and supplying for a phosphating process. They were to use this kind of a boiler because it was within the city. It's a small boiler, and the temperatures required were about 85 degrees. And at that point in time, there were no heat pumps in the market, though. I mean, there were no technology that readily available in the market that could deliver these kind of temperature. So we did develop and deploy a system. Now it is delivering close to about 90 degrees C. And see the numbers here. We replaced electric heater. Now the heating bills as their baseline is reduced by about 72% because kerosene is now about 90 rupees per liter. This goes for 24/7 operation. And the more important thing, whenever you have a fired source on your premises, you need environmental permits, you need a boiler operator, you need a lot of those regulatory requirements, whereas this system is like your chiller, which means that you don't, in addition to the soft benefit, in addition to the hard benefit of these numbers, you also get a soft benefit of not having a lot of regulatory and cleanliness issues. So to put it in perspective, before the heat pump, their annual bill was about 83 lakh rupees. And the current bill is about 21 lakh. And we did it in two places, a plating shop, which is electroplating. And this particular shop does a lot of components that go into automobile systems. And similarly, we implemented one more in the phosphating line. Again, data, we have an online monitoring system there. Just to give you a data from there, this is from October 2019 to January 2020. And heat pump, you can compare the cost of heat pump and more importantly, the decarbonization potential of heat pump. Compared to electricity, right now it is still appearing a little high when compared to maybe natural gas or LPG or diesel. The reason is because we are taking grid electricity, which is at an emission factor of 1 kilogram of CO2 per kWh. And if that electricity is from many of our green sources, this is going to be one of the lowest carbon sources for industrial heating. And that is the biggest opportunity we have for decarbonizing industrial heating. So now it is economically sensible and also have a carbon footprint potential. The innovation is also required. Here, I just give you one example of how the unknown technology was taken to the market. So we worked with a clean tech financing agency, which supported the funding. The project is deployed on a PPA mode, which is very similar to your solar power purchase agreement. We do have an OEM through whom we technology transferred and they do the operation and maintenance. And we kind of made with this project energy efficiency bankable, because a lot of times the challenge is not only technology, but it is the entire ability to deliver the solution, which also means making the technology bankable. So I give you one more example before I close up my presentation. Here, it is not just heating. As you know, the technology provides both heating and cooling. And this is where the biggest benefit really comes in, because in this particular case, you can see here, it was deployed with the heating tank and the cold tank. And both of them were deployed to the process. So on the heating side, we were eliminating LPG. On the chilling side, we were eliminating a chiller that was dedicated for a particular process with the cold water generated by the heat pump and integrated with a nice thermal energy storage system. Is basically a hot water and cold water tank. So that kind of integration is what, in addition to the technology itself, is what really helps us drive the benefits much more than just the technology itself. Here I have given only the data for the heating side, but the cooling side is equally impressive, and the overall payback of this project was less than 1 year. So the challenge most people have is that most of the energy system is designed for steam. So far we talked about hot water. So what if your need is steam? So we do have now technologies that are reaching commercialization. We have built one system. We are about to deploy it for testing. So this is for steam requirements up to about 120 degrees C. And you can again see the cost of steam. This is a metric that industry uses quite a bit. And here it is much less than about a third of that of diesel, and HFO, because it's a dirty fuel, it is subsidized, it's still cheaper than HFO. And you can see here, we are already quite competitive even in steam generation. So, and the reason why I think this is a good approach is because most of the time people in the industry generate steam at a high pressure and consume at a low pressure. And with this, you can eliminate that step. Again, soft benefits of not having boiler regulators, IBR, all of that comes in. But in this particular case, we do, and we are in the process of getting it to more and more applications. So I just want to conclude my talk saying that it is a technology for decarbonization, and we are in the process. This is just a few prototypes that we did in our lab, sent out for deployment. So what we are really waiting for is just to get our boiler fired. Thank you very much for the time, and look forward to your questions.
Thank you very much, Dr. Satya. Do we have some questions among the attendees who have rejoined us? Can you raise your hand?
I have a question. Can I ask?
Please go ahead.
Yeah, so, Prasanta, why has heat pumps not taken off? I mean, the chillers and the air conditioning system has been there. We haven't heard so much of heat pumps being used. Whereas what you are saying, it is no more complex than basically a chiller. Why has it not taken off in the industry?
Yeah. So there are a couple of reasons. Historically, in Indian industry, at least, the fossil fuel has been quite cheap, and the capex requirement for heat pumps was being higher. The second reason is also that availability of power somehow a lot of times was seen as not being there. The demand availability. So there has always been a electricity shortage as opposed to having fuel availability. So that drove what happens in India. But right now there are enough indications that we should push for this forward. In fact, in Europe, heat pumps are given the status of renewable energy, and you do get renewable energy credits for employing heat pumps. And recently in California, there is a legislation that's coming up which says natural gas boilers for even domestic heating should be replaced with heat pumps. So there is a trend towards electrification of process heating, but I think we all need to probably work on it even more.
Thank you. We have one question coming from Mr. Ashish. Can you unmute yourself and ask your question, please?
Am I audible?
Yes.
Okay, so my question is, when you calculate the cost of this steam from this heat pump, at the overall cost, are you looking at only the cost that you are in developing this? So how are you doing the cost estimation?
So there are two ways. When I'm doing a greenfield project, I'm only looking at the overall cost, operational cost of steam, because you are anyway wanting to implement a steam generating system. So when we do a brownfield project, we do look at incremental capital cost investment from the for going towards the heat pump also, not just the operational cost, but also the capital cost requirement.
Okay, thank you.
Thank you. I've got one question which is not far from this one neither. When you showed us the graph with the price of electricity regarding the source from diesel to etc., you show a very low cost for the solar panels, solar energy. But we know that this cost can be quite discussed because the life duration of the solar equipment are not the same as a generator and everything like this. What is the life expectation of a heat pump?
So typically, it is as good as any chiller air conditioner system. So normally 7 to 12 years, depending on the temperature and operational conditions. So normally the depreciation that we have is we write off the asset by about 10 years max. That's the normal rate at which it is depreciated.
Okay, thank you. Okay, it looks like no other question for the moment, and we'll take question at the end of the session if something else comes. So thank you very much again, Professor Satya, and I'd like to invite now Dr. Johnny Deschamps to go for his presentation. Over to you.
All right, it's okay. Everybody hear me? It's okay.
Yeah, we can hear you and see your presentation. That's fine.
It's all right. Thank you very much. So good morning and good afternoon, ladies and gentlemen. I'm going to present you a topical subject the hydrogen, and considering that we are in a context of collaboration, so I'm going to present you the hydrogen technology in France, and in the second part I will present you the activity that we have, the activity concerning hydrogen that we have at ENSTA. So just before to start, I forgot to introduce me. So my name is Johnny Deschamps. I'm a professor at ENSTA, École Nationale Supérieure de Technique Avancée. So ENSTA, it's a school of engineering, which is a member of Institut Polytechnique de Paris. So Institut Polytechnique de Paris, IIT Paris, it's a consortium of 5 schools of engineering. So a grouping of five schools of engineering. And we are at the south of Paris. We are approximately at 26 kilometers far from Paris at Palaiseau. So I'm going to present you to start the hydrogen sector in France. And before to speak about energy, we have to know that before to be a tool of the energy transition, hydrogen it's a raw material for the industry. Basically, 900,000 tons are used per year in the different industry in France. So basically, refinery, ammonia for the ammonia synthesis, the glass industry, metallurgy. And it is interesting to know that we have a big problem concerning this hydrogen. So because 95% of this hydrogen is produced by steam methane reforming. So basically by using fossil energy. And when we use this process, basically 10 kilograms of carbon dioxide are generated per kilogram of hydrogen produced. So it is a big problem. And after, if we consider the energy part, so the energy sector for the use of hydrogen, so hydrogen, if we reflect a little bit, hydrogen, it's an important energy vector, which could be very interesting to realize the energy transition. But before that, it is logic, but we have to produce it with free carbon. So we need a free carbon production. And green hydrogen production in France or everywhere in the world, green hydrogen production is very expensive. So basically the price of green hydrogen is 4 times higher than gray hydrogen price. So the gray hydrogen produced by using fossil energy. And before to start something, to do something, we have to propose something with very competitive price for green hydrogen production. Even if we can produce green hydrogen with competitive price, we have also to develop the infrastructure. So we have to develop also the industry to produce large hydrogen. And when we have produced hydrogen, we have to store it and to transport it. So we need also to transport infrastructure. We need also to build, to manage the infrastructure for storage, to develop infrastructure for storage and for the transport. So considering this problem, this context, France is committed to deploy the hydrogen technology, and we have a deployment plan, and we have specific priorities in this deployment plan. So we have three important priorities for this deployment plan. So the first one is the decarbonization of industry. So decarbonization of industry by producing carbon-free hydrogen, so green hydrogen production. So, and the question is to use electrolysis process. So electrolysis process, it's very efficient, but however, the electrolysis, as you know, it's quite expensive. So the price of one electrolyzer, it's approximately so it's between 1,000 and 1,500 per kilowatt. So you can imagine if we want to develop electrolyzer with 1 megawatt of power, it's quite expensive. So this is the first point. We have to decarbonize the industry. The second point, it's the development of heavy mobility with green hydrogen, with carbon-free hydrogen. So it's a context also of decarbonizing. And the third point of this deployment plan is to support the research, to support the innovation, and support the skills. So concerning this first point, so it is interesting to speak about this first point. So this first point supports the research, innovation, and skill. It's called in French PEPR, so Programme Équipement Prioritaire de Recherche, but basically in English, it means that it is the priority research program and equipment. And in this program, what we want to do, so what the friends want to do, this program deals with all the sector, with all the hydrogen sector. So basically, all the hydrogen sector, so the production, so green hydrogen production, the storage, the supplying and uses. So the storage is also very important. We have to develop performance storage media and also a cheap storage media. Similarly, for the supplying, we have to develop supplying units, so service station, if we want to work with mobility, and also the uses. So the uses basically for mobility or stationary application. So it means that we will use hydrogen. So for with fuel cell, or we can use also by combustion. And the second part of this priority research program concerns also the technico-economic aspect, which include the safety and the risk. So it is important also to speak about the economy of the hydrogen, especially in this case, because it's interesting to develop science. It's interesting to develop technology. But the economical aspect of the hydrogen, especially the hydrogen, is very important. And moreover, the safety and the risk. So, you know, the energy of activation of hydrogen is very, very low. So basically the order of 1 microjoule. So the activation energy, it's the order of 1 microjoule. So basically it's important also to have an idea of the safety and the risk. So I have presented the hydrogen sector in France, and now I'm going to present you. So before that, I just want to discuss also a little bit, I forgot, sorry, about the hydrogen sector in France. To satisfy this hydrogen deployment, we have important challenges that we have to be solved. And the first challenges is for the production of green hydrogen. So I explain you. And what we want to do, firstly, it's the improvement of the price and the time life of green hydrogen technology. So basically, to develop new electrolyzer. So basically, I explain you, electrolyzer is very expensive. So we need efficient electrolyzer and cheap electrolyzer. And we can use the renewable energy. So renewable energy can be also interesting to be implemented. So basically solar, wind, hydraulic. So to produce electricity, to inject inside the electrolyzer and to produce also hydrogen. If we can produce a cheap hydrogen, we have to develop also, as I said, the industry. So the industry to produce this hydrogen in large quantity, because we need, after a large amount of hydrogen, large quantities of hydrogen. So to supply for mobility, to supply for stationary application. Another point of the deployment plant is also the storage. Basically, we use a lot. So we use so the best storage media for the mobility currently is the hydrogen storage under high pressure. And we have to work on this technology, especially to optimize the price of the composite tanks. So basically, the composite tanks are very expensive, and it is useful to reduce the amount of carbon used. So because carbon is very expensive. Another one interesting point concerning the storage is the solid state storage of hydrogen. So storage by under adsorption, or storage with hydride, so with absorption. And we have to to improve also this technique of storage. So basically, it means to improve the condition of adsorption and the condition of desorption. So this is the context for the storage. Moreover, we have to compress a lot hydrogen because the volume fraction is very low. The volume fraction of hydrogen storage under pressure is very low, and we have to compress hydrogen at 700 bar to get an acceptable volume, especially for mobility. And another point that we have to work and to improve for the deployment plant, it's also for the mobility application. And so the first point concerns the price of the fuel cell. The fuel cell are quite expensive, so we have to decrease the amount of platinum catalyst inside. Moreover, we have to increase also the time life, and this one has to be these things has to be performed according to the performance of the fuel cell. So basically, if we want to do hydrogen car application, if we want to use hydrogen for cars, we have to maintain the performance. And we have to develop something efficient and something very cheap. Because you have to know, I think, that the hydrogen cars are very expensive. So in Paris, we have several hydrogen taxi, but this taxi cost approximately 75,000 euros. So you can see it's quite expensive, and it's difficult to develop at large scale for everybody. So we have to work on this price for the fuel cell, and after to work for the price also of the tank, to develop to propose something interesting, something cheap. So now I'm going to present you the hydrogen activity, research activity that we have at ENSTA according to this hydrogen deployment plan. So the first activity that we develop at ENSTA is concern the green hydrogen production. So we work of green hydrogen production from biomass. And we study the thermal decomposition of this biomass. So biomass, it's a natural compound, natural product, which is constituted by essentially by lignin and cellulose. And the first thing we do a chemical analysis of the biomass, and we perform this by thermal decomposition. And we have connected the apparatus of thermal decomposition. Basically, we do thermogravimetric analysis, TGA, and we connect with apparatus with gas chromatography and mass spectrometer. And finally, we can get the analysis of the different constituents of the biomass and also the product of decomposition. Basically, glucose, sorbitol, levoglucosan. And finally, after we analyze also the permanent gases during the thermal decomposition of biomass. So basically, for this experiment, we have a pyrolyzer, and we have connected with this pyrolyzer, with a gas chromatography. And we can directly compute, we can directly measure, perform the measurement of the hydrogen produced during the decomposition. So we have the chemical analysis, we have a gas analysis. So the decomposition, the gas produced, so essentially hydrogen. And finally, what we do also some calculation by using computational fluid dynamics, and we get the kinetics, we get information of kinetics, and we get the information of the kinetic mechanism of decomposition. So, and we can have some information of different systems. So the system of carbon monoxide, hydrogen, carbon monoxide, hydrogen air, carbon dioxide, water. So we can have different interactions, so different part of the decomposition process. And we can get also the different reaction. We can compute the different reaction of decomposition, and we can have some information about the kinetic. And so we perform this experiment with activity with different French industry. So, from example, Segula, 3EH2. It's a company which develops some heater for heating the building. Another one technology now it's what we develop at HENSTA. It's the green hydrogen production by using photocatalysis. What we do, we perform some synthesis of, and the doping of titanium dioxide, so synthesis of photocatalyst. And what we do, we develop some mild synthesis, and metal nanoparticle doping with specific technique of doping under pressure. We develop a specific technique under pressure, static pressure or dynamic pressure. And we develop also some composite catalyst, doped composite catalyst. So we mix titanium dioxide with MOF, and we mix also titanium dioxide with biomass. And we can get also, we can study the influence of hydrogen production. So we perform this activity in collaboration with Paris Saclay University, basically the Institut Chimie Physique d'Orsay and the Commissariat of Energy Atomic, CEA. So this is the part concerning the production. We work also on the storage, and we work on the storage and in porous material, in doped porous material. So we use the MOF material, metal organic framework material. So three-dimensional unit constituted by metallic ions, which are linked by organic ligand. And we develop some specific technique of doping. So we associate carbon, activate carbon, carbon nanotube, activate coal, with metal, with different metal nanoparticle. And after we perform some hydrogen adsorption measurement. So at low temperature, at ambient temperature, and under pressure up to 150 bar. So we perform thermogravimetric measurements. So we have magnetic suspension microbalance. And we can see that we have some interesting result with the doping. So we can multiply by 3 the amount of hydrogen stored at ambient temperature. So we don't reach the DOE target, but we make some improvement, especially for this type of storage, because the most important problem concerning the adsorption is to get something suitable to store at ambient temperature, because it's very easy to store at low temperature at 77 Kelvin, but at ambient temperature, it's quite difficult to get a big amount of hydrogen store. And this is the most important challenge that we want to resolve, especially concerning this adsorption in porous material. And finally, the last activity that we have at HENSTA is about the use. So the hydrogen combustion. So we study the hydrogen combustion. So hydrogen combustion is quite interesting because we use for the production of heat, for the heating, and it's used also in the aerospace domain, in the aerospace industry. And what we do at HENSTA, we study the hydrogen combustion and its gas mixture. So basically syngas. So we mix with carbon dioxide. We mix with methane, and we see we see the effect of this amount of gas in the mixture. And we perform the measurement by using a heat flux burner. We have developed a heat flux burner. And we have associated with burner with high resolution fast camera, and we can get some image of flame. We can also perform some measurement of temperature, structure and flame speed. So we can have all the details of the combustion, so structure and flame speed, the temperature, and the condition of the combustion. And also we can get with all this information the mechanism of the combustion, the mechanism of decomposition, and we have also some kinetic information. So associated to this, as I explained you at the beginning, the hydrogen safety is very important, and we performed some study concerning the hydrogen safety and the risk, especially in the building. So we have some specific contract with industry, with nuclear power plant to study the risk of hydrogen, propagation of hydrogen or something like that. And we performed this study with different collaborations with French industry, so in BDA, aerospace domain, and also some specific company which develops some heater, so for the heating of the building, and something like that. So I have presented you the hydrogen, so the hydrogen sector in France, so and the activity that we have at ENSTA. And as you can see, France, like other world country, it's engaged, it's committed to the development of the hydrogen technology. We have different plans of action that we are being developed. And we work, the research, French research is working on the most important challenges of objective of each part of the hydrogen network, hydrogen technology. So the most important part is the green production, the storage, the supplying and the uses. And finally, you can see that we have a lot of work. A lot of work is needed to reach the different targets. Especially in terms of price and also in terms of efficiency. And finally, with scientific collaboration with India will be welcome because we are in the context of collaboration. So you can see that it can be very interesting to get different collaboration on these different subjects. So thank you very much for your attention.
Thank you very much, Dr. Johnny Deschamps. I can see Professor Ashok wishing to ask a question. Maybe we can start like this, Professor. Yeah, please unmute first.
You have been talking, and we have heard several talks, which talks about we need to significantly reduce the cost of green hydrogen. Now, we all agree with that. What are the next steps? How do we move to reduce the cost? What are the key components we need to reduce the cost of green hydrogen?
The key component to reduce the price of hydrogen, it's a very good question. A lot of researchers are working on it. So basically, we have to develop a very efficient electrolyzer. And as you know, in electrolyzer, we use catalyst, a noble metal catalyst. So it's similar for the fuel cell, and we have to reduce the amount of the catalyst. So it is the most important part, to reduce the amount of this catalyst, and also to have a more efficient electrolyzer, and we have to also improve the time life. So this is the condition, but now a lot of researchers are working on this. And also, I didn't mention, but the green hydrogen green hydrogen is also very expensive because electrolyzers need electricity. So we have the price of electricity also. It's for this reason, renewable energy are very interesting, especially to produce green electricity and after to inject electricity in the electrolyzer. So this is concerning the electrolysis, but we are also different action to produce green hydrogen. So I mentioned the biomass. So biomass can be also a solution because it's a renewable energy, it's a green energy. So it's we can also work with biomass to try to develop something interesting concerning the green hydrogen.
Okay, thank you very much. Have we got another question? Can somebody raise a hand? Let us know. Otherwise, I've got one on my side. You have mentioned several times how explosive and how dangerous potentially is hydrogen. Also, the cost of the cars, the taxi hype, the brand hype, etc. in France. Is it? Shouldn't we focus first for fixed facilities using hydrogen before going for mobile vehicles? Shouldn't we focus first on something like to supply energy for factories, facilities, and things like this?
All is important. So in the deployment plant, you have seen the most important is the decarbonization of the industry. So it's the fourth point. It's quite interesting. But also the mobility is also very interesting, basically for the pollution and everything. And this is the second point of that I mentioned concerning the deployment plan. It's to decarbonize the heavy mobility. So this is the second point of the deployment plan, to decarbonize the heavy mobility. So yes, it's I think the most important is to decarbonize at the beginning the industry, but also the mobility. It's quite important. And it's approximate. It's related to the precedent question, to the last question. The price, it's related to the price of the fuel cell, because the fuel cell is necessary to use some catalysts. So fuel cell is quite expensive. We have also to work on the time life of the fuel cell. And there is also another one problem also for the storage. So storage, the tanks are also expensive. So finally, we have an expensive setup. So we have to work. It's for this reason I mentioned we have to work on the green hydrogen production. We have to work on the storage, and we have to work on the use. So it is the totality of the technology finally.
Okay, thank you. Thank you very much. Maybe Professor Asad Sahir from, you wanted to say something, you put something in the chat box. Oh, okay, it was maybe just a comment, so I will read it for all of you. So Professor Asad Sahir was from IIT Madras, was thanking you for your presentation and just encouraging you to go for collaboration with India. And yes, this is what we will expect. So don't hesitate. Before I forgot, two small things to add. I will let you my professional email address in the box. I can't disclose the email address of the other one, but in case you want to get in touch, don't hesitate to send me an email. I will pass you my email address in the chat box. And just let me know with who you want to get in touch, and I will forward your email to different people so connection can be made. Thank you again, Dr. J. Deschamps. Thanks for this very interesting talk. And before going to the next speaker, I would like to say that I won't be your sole moderator today. So Anson Sando from the IIT Madras Research Park will join me also and later. So we'll share the floor to moderate and to welcome the speakers and to relay the questions. But so far, let's go for the next speaker, and I'd like to invite Dr. Ramachandra Rao from the IIT Madras Research Park to come and to join, be connected from the Research Park platform. Dr. Ramachandra, over to you.
Bonjour, François.
Oh,
There is my presentation.
just share
Screen. This one. Okay, so we get started. Yeah, thank you, Professor Ashok, for.
I want a single slide so that you don't have.
Yeah, I'll just. Yeah, I can hide it. Yes. So, thank you, Professor Ashok, for asking me to give a presentation to share all the excitement that we're going through in material aspects of green energy, solar energy, power harvesting, And towards the end, I'll also be talking about these wonderful sustainable diamond coatings for a lot of energy applications. So, well, I belong to 4 centers, and each of these centers has at least 15 to 20 faculty members from various departments in IIT Madras. So this is a beautiful green campus, you know, of French collaborators and counterparts. When you happen to be in Chennai, please do visit us. That's our center where all these activities are going on. Well, if you look at the generations of solar cells, you know, we have several options, you know, all the way from monocrystalline silicon, where you have efficiencies of the order of 27% now, polysilicon, and there's a set of thin film based photovoltaics, A-silicon, CDTE, CIGS, and its alternatives, CZTS, which is not quite successful because of material problems. And then you have a whole lot of alternative materials these days, you know, dye-based solar cells, quantum dot based solar cells, and organic photovoltaics, and you know, the perovskite based solar cells. I think the perovskite based solar cells are going to rule the roost probably in the next decade or so. So very quickly, Professor Ashok must have highlighted all these things about the solar potential in India. There's a huge potential to tap in India in terms of the requirement and also the capacity of energy requirements. It's of course, solar power is turning rural India bright and shining, and there are several government funding programs, you know, especially from Ministry of New and Renewable Energy and Department of Science and Technology, which is one of the main funding agencies, and DST also has a solar energy research initiative with which we could establish a wonderful center here. Yeah, India's smart villages are centralizing solar power. There's a lot of nice activities all over the country. I think Rajasthan produces the maximum amount of solar energy using you know, PV panels, but unfortunately, we don't have indigenous technology to develop these panels. That's always a big concern. That is the reason why DST wants indigenous development of these technologies right from ground zero. So that's how Solar Hub was born 3 years back. This is the culmination of this center happened because of several individual projects that many of our faculty members have successfully completed in the last decade, and DST, Department of Science and Technology, has realized that IIT Madras has the strength in terms of materials and all the engineering aspects, yeah, solar thermal, solar photovoltaics, energy storage, etc. So they called us and said that they would like to establish a southern solar hub here, and then it has happened, okay, with the funding of about 40 crores to start with. This is we are in the first phase. By next year, we'll be completing the first phase, and we have been quite successful in dealing with the objectives set in the first phase. Yeah, quickly, we have one in the western part, one in north, one in the eastern part of the country, and this is one of the last hubs that have been established, but already DST is thinking of making it as a center of excellence because of the productivity that has come out of this particular you know, solar hub. So what do we do here? We work on the basic aspects, that is the research work package and the technology work package. The TWP deals with fabrication of single heterojunction solar cells to produce efficiencies close to 20-21%. And then we also have Professor we have my colleague from mechanical engineering, T. Sundarajan, heading the solar thermal initiative, where he uses solar energy for storage purpose. Okay. On the research front, many of our group members from chemistry and chemical engineering, they focus on DSSE, you know, dye-sensitized solar cells and perovskites. And the whole idea is to integrate and make a tandem solar junction, whereby you can increase the efficiencies close to 27%. So there are 4 verticals: photovoltaic, solar fuels, energy storage, and solar thermal. And we have a very active a team from various departments, about 60 staff members. We also have other universities and other IITs in this program. We have the photovoltaic program, as I mentioned. Solar fuels is run by GRR, and then energy storage by Srinivas Jayanti, where they look at alternative vanadium redox batteries. These are bulky ones, but once energy is stored there, the energy storage can be there for a long time, right? And Professor TS deals with solar thermal, where steam is used for cold storage and desalination also. Okay, these are some of the facilities already established in IIT Madras. There are many more. And then one of my colleagues from the mechanical engineering department, Dr. Satyan, he specializes in polishing silicon wafers. I'll highlight a little more about the production of silicon wafers. So his idea is, in order to remove the defects from silicon wafers, the best is to start with the thicker wafer and polish it down. And this way, the mechanical defects can be eliminated from the wafers, which are used for depositing other layers. So let me go through what we look at in terms of material development. This is the work of my colleague from chemistry department, Mr. Raman. The problem here is in dye-sensitized solar cells. One of the problems is the high dye loading time. And he has come out through first principle calculations and a methodology whereby the dye loading times can be reduced enormously. And they also are in the process of synthesizing new dyes for better efficiencies. They could go all the way from 6 to 8 to now 12%. And he has established a very nice lab where he can do right from the production of dyes all the way to devices, a lab in our new academic complex. And another colleague of ours who is in the program deals with all the drawbacks related to perovskite solar cells. So the problem is we know that efficiencies of 25-27% could be obtained using perovskite solar cells, but these efficiencies are short-lived. You see a huge amount of deterioration as a function of time. So what Venkat's group has achieved is, they play with the molecular dynamics of these different perovskite molecules by adding a few more chains. It's their proprietary work, and then thereby, the degradation process has been arrested. It's a very significant contribution. So what we do on our side, as physicists and device people, and with my colleagues in the electrical engineering department, we take those molecules and make devices, right? So that's one of the areas where we focus on, as you know that I think maybe it's a matter of another 5-10 years where you start seeing perovskite-based solar cells in the market, but still the problem is scaling up. That's where one can effectively collaborate. These perovskites have high efficiencies. The MTL and ETL layers, band gap can be tuned easily. They have large absorption coefficient, and the mobilities also can be tuned easily. And this is, as you can see here, one of the devices that we made out of the molecules that were made by our chemistry colleagues, and we see efficiencies consistently of the order of 14 to 15%. But the problem is the device area is very small, and scaling up is always a big challenge. I want to mention about this here. Not only India, there are many countries that lack silicon wafer production. We all are dependent mainly on wafers coming out of China, and sometimes they're not of good quality. In fact, we have all the expertise in growing silicon wafers in the form of ingots. cutting them, a lot of crystallography is involved there, and then slicing wafers to all the way to the polish stage. Okay. Very quickly about Oxide Electronics, because our group also focuses a lot on Oxide Electronics. It's all about the marketability of Oxide Electronics in terms of LEDs, displays, UV detectors, and sensors is enormous, right? And why oxides? Because again, because of the tunability, you can prepare these oxide materials at lower processing temperatures, and you can also have plenty of choice when you're looking for different devices with that require different electronic mobilities. And today you're looking at various low power electronics made out of these oxides for whispering gallery mode, lasing emission, zinc oxide based UV detectors, and flexible field effect transistors. Yeah, that's where you see that when you have oxides, you can cover mobilities all the way from 1 to 50 centimeters square per volt per second. So we in our lab use pulse laser deposition, a very effective tool to deal with all these functional materials. You name functional materials, multi-component system, laser deposition is the technique. And then you see we made even LEDs using these one-dimensional nanorods, and zinc oxide again is a very good alternative for gallium nitride for UV detection, and you can make very effective LEDs also with zinc oxide based devices. And then when it comes to power harvesting, this is again a very important area for MEMS applications and power harvesting. There's nothing like a piezoelectric material, a PZT, lead zirconium titanate. We are capable of making large area PZTs that give very consistently high values of polarization using pulse laser deposition. As you can see, we have demonstrated flexing those PZT films and generating power to light up LEDs. We have also made underwater sonar devices for our defense applications. Okay. Now, this is very exciting. So diamond we call it the ultimate engineering material for energy saving, for mechanical, electronic, biomedical applications. Okay. Why diamond? Because it has the highest thermal conductivity, higher than even copper. Its thermal conductivity is 4 times that of copper. It's the hardest material, and it is also transparent to all the way from mid UV through visible to infrared radiation. What's the advantage of that? You can coat diamond on solar panels that power our satellites in the outer space. The problem with those panels is, even though they're marked for 25 years of operation, because of the continual bombardment from extraterrestrial radiation, the performance deteriorates. But you need a coating that still allows the visible radiation, but then it has to cut off the high energy radiation. So diamond can do that. And diamond coatings also act as mechanical wear resistant coatings because of the high hardness of diamond. So all these things we deal with, So and most of the electronic components use diamond as heat spreaders. All the electronic components that work almost 24/7, you need to dissipate the heat away, and diamond is the best thermal spreader. You can use it for hardware coatings, and of course, the physics of diamond, doping in diamond is very exciting. So the next generation quantum computers are based on NV centers in diamond. So we prepare all these diamond samples in our lab, all the way from micro, nano, and ultra nano crystalline diamond. We can also make single crystalline diamond layers. And so about sustainability now, right? Now you see, the usage of aluminum alloy and aluminum-based composites in automobile and aerospace sectors are increasing substantially, due to their better energy-saving capacity, and also because of the low weight that improves the efficiency of the engines, or machines. But the problem is the following: if you look at the statistics, studies show that about 2 billion gallons of cutting fluid is used or wasted every year for machining applications. So when you're machining a mechanical tool, using a mechanical tool, it produces heat, and you have to use this cutting fluid, and this cutting fluid is dumped into rivers, and all the drinking water is contaminated. So how do you deal with this issue? So now it's all about dry machining. How do you do dry machining? You need to have a coating that also dissipates heat away, so that you need not use the liquid cooling. So the best coating for this purpose is you have diamond in the form of saving the tool from wearing out, because it's a hard material, and because of its high thermal conductivity, you can also use it as a heat dissipator. And depending on the smoothness of the coating, it can also act as a lubricant. You see how many different purposes it can serve, right? So we have developed all this technology in our lab in IIT Madras with my colleagues from other mechanical engineering and the other departments. We work closely with two industries in two industries that have that manufacture automobile compounds, ceramic components, and our coated tools show an improvement in mechanical the life of the tools by almost 12 to 15 times improvement. This is very significant, right? A plethora of applications. You know, we look at the mechanical applications. We look at making diamonders for optical windows. For we work closely with our space research organization. They need these optical windows, radiation sensors, and diamond coatings are also biocompatible. No, we work with medical fraternity in Chennai, where some of these diamond coatings on dental implants showed that even after 3 months, there is no bacterial formation when diamond coatings are there on dental implants. And then one of the very exciting things that we are looking at now is using diamond electrodes for water purification. We also have a startup in our research park, and then what has come out of hard work in the last 3 years is probably by next year, we'll have a product in the market that is using diamond electrodes indigenously. This is another big area. I think in India, there's no company or no research where this kind of development has happened. So all this has been developed in the lab, and we are taking it all the way to industrial applications. You see, we have even shown that the first device that we're going to come out with is a sanitizer unit, handheld sanitizer unit, where water itself can be used as a sanitizer. That's one thing. And second, you see that we have taken industrial waste, right? This is from a textile industry. Using these electrodes that we indigenously developed, you could see that this dirty water, industrially contaminated water, can be completely purified in about, of course, it takes 2 hours at this scale, compared to the traditional, conventional electrodes. So we have a big project from the government of India to develop cheaper electrodes for Indian industry, and that's what we are doing. We are hopeful of succeeding in that front. And you see that we start with this methyl orange solution here, just to demonstrate at the lab level, and then we are able to clean it up completely. So it's called the dye-contaminated water can be cleaned up, and this way, not only industrial dyes, pharmaceutical waste is also a big concern in many countries. No, water contaminated with pharmaceutical waste. So diamond electrodes can deal with that, right? Okay, so we have won several awards, and recent one was the Dare to Dream Award initiated by the Prime Minister of India, where we have shown that these diamond coatings could be used for hypersonic missile technology. And then, okay, the next big thing is the physics part of it. I don't want to go into all those details. NV centers in diamond for quantum computing. So thank you.
Thank you, Dr. Ramachandra. Do we have some question coming from the audience? Can you raise your hand and ask your question, please?
I can.
Otherwise, we're having some already here. First question was about the life expectations of these perovskite cells. Have you got some comparison to more traditional ones?
Yeah, so the comparison is, when we use the standard ones, standard perovskites, you get these efficiencies, high efficiencies, but then within a week or 2 weeks, the efficiency is half. It becomes half. But now with these new molecules developed by our colleagues, even after 3 months, we see no degradation. So that's so it's not about encapsulation. Encapsulation doesn't work. So because the degradation is inherent to these molecules. So these people put some a new attachment to those chains so that the internal degradation stops. That's the key there. I can't give you more details than that, but it's 3-4 months, there is no degradation.
Okay, thank you. Another question we received was about the recycling of these cells because they are containing some elements which need to be managed carefully. What about the recycling when the panels are reach the end of their life? Recycling
of panels. I think that's one of my colleagues is looking at it. Yes, recycling can be done. It's not an issue. Yes.
Okay, thank you. Have we got some other questions? If not, I would like just a few seconds to pass the lead to our host, Tejas from Streamy Company, who would like to make a picture with everybody. Please state Dr. Ramachandra, with all video on. They would like to take one more picture. Can you stay a few seconds?
Okay.
If you could please turn all your video on.
Turn all your videos. I think your video is on.
Sure, but can also come. Yeah.
No, my video is on.
Oh, yours is there. Okay. I think if it goes to multiple,
then everyone has to log.
They will manage on the side. Don't worry.
Tiles, it's better. Okay.
Okay, Tejas, is it good for you?
Yes, it's perfect for me. Thank you.
Thank you. Thank you. Thank you very much.
Thank you. Yes.
Thanks a lot. Thanks again, Dr. Ramachandra. And I would like now to invite Dr. Jean-François Guimol to make his presentation. Over to you.
Hello, everybody. Thank you for the invitation to present the research in France. So I try to move to full presentation. Just tell me if that works for you. Can you see the slides?
Yeah, but you must change. We are in your view. You must modify the view because we are seeing your next slide.
Yes, sure. Sorry for that.
It's okay.
So I try to. Because I have two screens. Maybe.
You can just use the diaporama as a presentation and then modify. Select the screen you want to share.
Yes. That would be easier indeed. So okay. So I will share the screen. Okay.
No, it's okay. Paramètres d'affichage et vous modifiez. En haut, vous avez paramètres d'affichage. Non, c'était bien. Restez comme ça, mais paramètres d'affichage.
Ok, alors je repartage, pardon.
Voilà. Pas de souci.
Partager. Et j'ai paramètres d'affichage. Ah, d'accord, ok. Comme ça? Non?
C'est parfait.
Ah oui, d'accord, ok, très bien. Sorry for that. So thank you again for the invitation. So I'm Jean-François Guimol. I'm a research director at CNRS and head of a joint research unit between academia and industry partners, so including CNRS, Ecole Polytechnique, and Chimie Paris-Tech, and IPVF, which is a consortium that I will explain just in a minute. So Actually, this is a center that's located near Paris. It's we have gathered teams from several labs, whether from industry, from EDF, Total, now Total Energy, CNRS, Ecole Polytechnique, and other partners like Air Liquide or Ribert, in a single site on Plateau de Saclay, so not too far from ENSTA that you just heard about. And maybe similar, and as an echo to the previous presentation, also this is a center devoted to the development of photovoltaic energy in the framework of the energy transition in France that has been subsidized also and supported by the state, the French state. So there are about 200 industrial and academic researchers here, and with a lot of, well, with a nice platform that I will present. So in terms of context, photovoltaic has been growing steadily over years. So it has been in the noise for many decades, unless except for those who were studying this carefully. But the price now, as we know, has been historically decreasing quite fast, actually. And the PV electricity is more than 2% of the worldwide electricity, maybe close to 3% now, with a lot of power installed, efficient modules. And all that growth has been supported by research. And you see here on the chart that basically, on average, every year, there is about 0.5% gain in efficiency of the modules in the lab that has been also translated into industry. And together with the economy of scale, increase of performances has led to a wider acceptance and opening of markets for solar energy and photovoltaic solar energy. So for that, our institute, the Institute of Photovoltaic in Ile-de-France, has an objective to further that, to make photovoltaic still more available to everyone, and with, for instance, a flagship target to develop a market module with 30% efficiency, 30 years lifetime, and a cost of 20-25 cents per watt peak. So this cost is achieved, but not with the efficiency, and I will explain maybe, or we can discuss why this is important. So to support that, we have several programs, joint program of the Institute. One is on economy and market assessment to choose this economic target and to support that. But we have also research on really the material system, the device modules, so like perovskite silicon tandem, which is a hot topic, but also we look at low-cost 3-5 on silicon tandem cells with some interesting successes there. And we have also more, looking at exploring more tentative issues like making solar to fuel, so other use of PV as compared to electricity that I will not detail today. And we have also proof of concept of innovative breakthrough, and so where we explore more longer-term targets for solar photovoltaics. And then we have a support activity, which are also very important on characterization, reliability, we just talked about, and modeling. Reliability is also very important, of course, for PV. So if I look, so our challenges are really aligned with societal challenges. So it's really developed new materials processes for lower cost, higher performance, but also thinking about reliability and sustainability at terawatt scale of photovoltaics. We're trying also to push the limits, exploring ultimate efficiencies. So today's efficiencies are about 20%, but we know that from more basic studies or fundamental studies that we could reach 60% or possibly a little bit more for standard applications. And to support that, we also look at advanced materials. We look at advanced diagnostics also for PV application. And final activities also that we have a lot of activities, also training the next generation of researcher and engineers working in the field in our platform. So this is based on a lot of know-how on elaboration of photovoltaic materials with a lot of ability to grow different type of material by co-evaporation. This is a bit expensive, but can make very tailor-made and advanced materials. So that's used for chalcogenide, like CIGS, and also for 3.5. But we have also atomic layer deposition process that are able to make conformal deposition as just like as you see is for an example for nanowire solar cells. And we have also solution chemistry like electrode deposition, chemical bath deposition, drop casting to look for more large area, low cost also processes for solar cells. And we have some standard techniques like sputtering and many others. And we essentially cover a lot of the thin film technologies. So some of them also used for silicon technology, like in heterojunction technologies, for instance. So I forgot to mention, by the way, PECVD, plasma enhanced CVD, also for amorphous silicon. So if we look at the type of solar cells that we can make, so we have demonstrated on CIGS flexible devices, as you see here on the top left side, with a nice efficiency, close to 19%, close to 20%, with process that also we're getting rid of cadmium, which is, even though it's a small quantities, it's still a nuisance to have this type of elements in a device. We have demonstrated also fully solution-grown solar cells, like in that case, again, CIGS at 14%. And this is also interesting, so that's this material also, as was shown, also discussed for perovskite solar cell, is also something that can be done also in solution. For the in terms of perovskite solar cells, very important topic in the institute. There is a very big effort here. We have shown demonstrated about 20% solar cells, 16% mini modules, as you can see on the bottom bottom right. And we're also working on bifacial tandem cells. So we have 17% semi-transparent also perovskite solar cells. And so, of course, their higher efficiency have been demonstrated elsewhere, but our focus is also to demonstrate this on processes that can be scaled up. And so we are working on mini modules. And finally, another area where we have also excellent results is on 3.5. We have developed top cell for that could be associated to silicon with a new type. So with a mixture of aluminum gallium arsenide and aluminum gallium phosphide, making an heterojunction solar cells in association with C2N. And we have also we're also working on ultra thin solar cells to reduce the material and to the material usage. That can also, by the way, be interesting for space application with 20% gallium arsenide solar cell that is actually 10 times thinner than the standard. We're also working on a new concept, and I will show that a little bit later. So we're also involved in European collaboration networks. For instance, I show you 2 European projects that we are being active on. So this is, for instance, a project that associates making tandem. Tandem is the way to associate materials. You know that for single junction solar cells, the limitation is really at 30%. Best solar cells are actually very close to that, like gallium arsenide at 29% have been demonstrated. So now really to go beyond that, one has to associate several materials to better convert. We have to have better efficiency in conversion of the solar spectrum, the available energy in the solar spectrum. The preferred way is making tandem. And here, so we have 2 projects on European projects. One is having perovskite on CIS associated to thin film technologies. So either monolithic integration or for 4 wires, 2 terminal type of solar cells. So this is going nicely, and we have demonstrated already nice results there. And another one is associating perovskite solar cells with OPV, organic photovoltaic, also in a European consortium. And that's with the idea to use and to extend the use of solar photovoltaics, not only to large area power plants, but also to building integrated. And this is in this case having a semi-transparent tandem cells that would be at the same time efficient, but that could be used also for windows. Other examples that I'd like to show on our know-how and expertise is about characterization and modeling. And we have developed a lot of optoelectronic characterization, and an epitome of that, or a good example of that, would be luminescence imaging, where we have imaging capabilities on spectral. So that means we can have spectrally resolved and spatially resolved spectra of solar cells. I'll show you how important that is. But also we have lifetime imaging that we have developed, and combining the two, we are really able to access a lot of transport parameters locally resolved in solar cells. And we had also some success with commercial application of some of the technologies that we have developed. We have also a strong activity looking at energetics at interfaces, looking at band lineup, interface design, interface treatments, including some work at synchrotron facilities. And then we have also some fundamental studies. So we put that in terms of modeling and also characterization to explore new solar cells concepts such as photonics, advanced photonics, that enabled, for instance, to make these ultra thin gallium arsenide solar cells, but that's also used for other systems. Okay, so for instance, showing what we can do with PL imaging, we have developed a photoluminescence imager, where using some modeling of the systems and designing and calibrated or advanced photoluminescence imager, we have spectral result. So you see that we have a spectral result here. You have on the bottom left gallium arsenide solar cell, where we have at each point able to extract a spectrum, which is also calibrated. Often PL spectrum are in arbitrary units, but this is it. We really count the number of photons, and from that, we are able to extract the chemical potential of radiation, which can be related actually to the open circuit voltage of the solar cells. And you can see on the table on the upper right of the slides that we can actually, what we can measure optically is really very close to what can be measured electrically on the same device. So if we illuminate a device and we look at what we extract from the PL spectrum, which is again spectrally, especially resolved, it's really related to what we can measure on average on the solar cell. If we can do that, we can also, by the way, reconstruct IV curves. And as we've shown, we can essentially measure the efficiency of a solar cell by looking at it. So we illuminate and we look at the luminescence, and we can infer the efficiency of the device. So we have access actually to the parameters of the conversion. What is also important is sometimes, or most of the time, also to have access and especially resolve the kinetic parameters of the conversion process, photovoltaic conversion process, such as surface recombination, mobilities, lifetime of the photogenerated carriers, and so on. And so we have also demonstrated on gallium arsenide, on perovskite, that from lifetime imaging, so we send a pulse on a wafer, on a solar cells, and we look at the decay, spatially resolved, and we can solve the transport equation and solve also for the parameters of the solar cells. And that's also very, very useful. So with a single experiment, we can do it. Of course, if we combine, we've been able, for instance, for perovskites, to look at all the electronic properties in aligned perovskites, and look at photon recycling in the system, looking at the transport of electron and holes, carrier diffusion, and singling out the different phenomena that occur in such a device. Using also this same type of technique, we can also study solar cells in technology that are very difficult to study because the device don't really exist. But we were able to study and demonstrate the first hot carrier solar cell, showing a hot carrier solar cells that were working with electron at 600 Kelvin, and already having some showing that this would lead to some extra voltage gain in these devices in such 3.5 based device. So of course, these are very expensive. It's just a proof of concept, but we could demonstrate that some gain from using hot carrier in solar cells. And finally, we also, for what I wanted to discuss today, so we also work on stabilizing devices, and there, you know, that in solar cells, especially in thin film solar cells, the interface is a big part of the device. And we've been working in collaboration with other labs, but also we have a lot of work in-house, also trying to stabilize perovskite solar cells, which is an issue that's just been discussed, and looking at how tailoring interfaces can help achieving these goals. Such instance as looking at the whole transport layers, looking at the electron transport layers, and so on. And so we're doing that, and at the same time, we're starting to do some outdoor testing of the in-house made solar cells, also to study, but that's very new, and I don't have really much results to present on that. So with that, I'd like to thank you all, and yeah, just I would be happy to engage in discussion with you and see what can pop out as a collaboration also with our Indian colleagues. Thank you.
Thank you. Thank you very much, Dr. Jean-François Guimol. I received some questions, but do we have some of you on live who would like to ask something? Would you please raise your hand? Waiting for that, I will ask you one of the first questions. Coming back to these bifacial solar cells, what are the main concrete application for these?
Which one?
The bifacial solar cells.
Bifacial solar cells. Okay, so bifacial solar cells actually very interesting for some of the application. One is that you have a higher energy yield for a given surface, because you can take advantage of the albedo of the surrounding. And you know that, I mean, for a normal solar cell, you would just collect what is really on the device. But for bifacial, you can also benefit from the light that would be reflected on the ground and coming from the back of the device. This can add some 10 or 20% more power to the system. This can it's of course it's not made for on-roof application, or not. I mean, for individual houses, it's not adapted, but it's quite significant for, say, big power plants, where you can have a here with a large albedo, a ground with a large albedo that would then reflect a lot, and that would be interesting. So.
Hi, we have a question from the room here.
Hi, can you hear me?
Yes.
Yes. So you mentioned about CIGS based solar cells, right?
Yes.
What do you think about CZTS? CZTS came in a big way. It's a cheaper material, but then there are lots of associated defects.
That's right. I see it. You know, it's a bit. I think CZTS is interesting. It's still immature, and there are, you know, maybe it's in a situation where CIGS was 20 years ago or so, and it hasn't passed the level of efficiency that is expected for large-scale applications. So the way I see it is that, I mean, CIGS has proven, and after a lot of efforts, to be amenable to large-scale applications, stable, scalable, and so on. But you know, there is this expensive indium. So of course, if all that could be replaced by CZTS, it would be much better. But it needs some maturing still of the CZTS. But I guess that because the material are a bit similar, the effort that has been made and is still being made in CIGS research could, in the end, develop into better CZTS solar cells that could then benefit from all the scale-up effort that has been done on CIGS. And in the end, probably one would need for large-scale applications something like CZTS. I think CIGS would be limited probably to a few gigawatt, maybe tens of gigawatts worldwide because of this indium issue and gallium issue. But then one can expect that CZTS could, be a relay for the growth of such thin film, polycrystalline thin film technologies.
Okay, thank you.
We have one question in the chat.
Okay, so I see there is what are the simulation tools do we use for the material research? So actually we have an extensive material modeling program in-house. I haven't developed, but that goes from some ab initio research on material like perovskite that we need to understand better. We've done that also on chalcogenide, doing that also on silicon. So there is some ab initio. I would say most of the research is nowadays geared towards device modeling. That's optical modeling, obviously, for tandem is very important. And so we use some available tools, especially for nanostructure. If you want names, I mean, I'm happy to exchange on the names, but they wouldn't mean like RCWA software. We also developed a number of software for optical modeling, optoelectronic modeling, modeling of the characterization techniques that we use. But we also, of course, use commercial software for optoelectronic modeling. And I'm happy to share the names of what we use. But we also do a lot of in-house development. Did that answer the question?
Yes, absolutely. Sorry, we are two moderators and we have like a little miscommunication between us. Very good. Thanks again, Dr. Jean-François Guillemot. It was a very big pleasure.
You're welcome, and anyone I'm happy to answer emails, and I think the emails are shared from the participant list.
Thank you.
Thank you very much.
Thank you.
Thank you. Over to you.
Great, thank you, FX. So for our next presentation, I'd like to invite Professor Rajneesh from IIT Madras, who will be providing a presentation on carbon capture and sequestration. So over to you, Professor Rajneesh.
Okay, so I hope all of you are able to see my screen. Yeah, so today I'll be talking about a little different stuff. I've been hearing a lot of hydrogen and solar. So today, now I would talk about some process development for CO2 capture and sequestration. We work on certain United Nations sustainable goals, which are listed at the top of the screen. And I belong to Indian Institute of Technology Madras. I'm a faculty in chemical engineering department. My email ID is listed over here. So for any further contacts, you can actually mail me on this. So in my research group, if you see here, there is this CO2 capture, utilization and sequestration pathway drawn. And if you see here, there is a green line. So I typically follow this green line. And there are other options like this gray line, which others in my team work. So in my lab, we don't work on these lines, which I call gray line. One is direct capture from air. I personally believe that the CO2 capture from air is going to be mostly done by chemical route. Physical adsorption will not work there because the concentration of CO2 is going to be significantly low. I don't work on this. Most of my research focus on the point source of CO2 emission, and most of my processes are supposed to capture CO2 from these, where you have a concentration of CO2 from 10–15% to up to 70–80%. And then I also work on the transportation part of it, how you transport the CO2 which you have captured, and then ultimately how you are going to sequester the CO2. What are the options which we have while we sequester the CO2? Mostly in India, if you talk about, there are basalt rock formations, which requires long-term and very slow CO2 sequestration. And under the seabed is what I'm going to talk about today.
EOR?
EOR, I'm not talking today, but yeah, there are options of sequestering CO2 and then getting some enhanced one recovery by doing that. So if you talk about CO2 capture technologies, there are two different sources of CO2. One is gas mixture with high partial pressure of CO2, and the other is a gas mixture with low partial pressure of CO2. Typically, when you are trying to gasify the coal or any other fossil fuel, the CO2 coming out from this will be at higher CO2 concentration. And if you are doing this post combustion, like if you are burning the coal for utilizing energy, since it is this burning of coal or combustion of coal is done in excess of air, you typically produce huge amount of nitrogen and oxygen along with the CO2, which is the product of combustion. So capturing CO2 from these routes, from the gases coming out from the power plants of either coal fire power plant or any other fossil fuel power plant, you will have to deal with chemical absorptions. And there are liquid solvent amine-based processes which are very mature. There are other materials, but the total cost, if you talk about here, the energy cost for absorption by chemical route is around $14 to $15 per ton of CO2. Membrane is another upcoming area, which is basically it's quite expensive, so I've not given the numbers over here. If you have CO2 with higher concentration of carbon dioxide in it, a mixture with higher concentration of carbon dioxide in it, you can go for physical absorption or adsorption processes. Cryogenic distillation is another approach. The major cost in this is going to be bringing down the temperature of the gas mixture. Typically at lower temperature, physical absorption or adsorption will work better. And this is why the cost you see here is around $27.8 per ton, which is twice as much as what you see here. So this is the capture cost. Here you don't take into account the regeneration cost. In this case, the regeneration cost is going to be much larger than $13.9 per ton. But while you are using physical adsorption process, the regeneration cost is going to be much lower because the capture, the strength of interaction between the CO2 and the solvent is much smaller. In this physical adsorption process, there is another process which is called hydrate-based gas separation process. My research work is mostly on hydrate-based gas separation process. I'm going to talk about how exactly this process captures the CO2 from associated gases and how economical or technical feasible this particular process is going to be. So in nutshell, if you see what we are talking about, capture of CO2 from a mixture, you can have a mixture of CO2 with hydrogen or with nitrogen or CO2 and methane mixture. So what we are basically using, we are using just water, nothing else other than water. So we mix water and gas, and as soon as you mix water and gas at certain temperature and pressure conditions, you will form these ice-like crystals. These are physically similar to ice. Chemically, there is only one difference, that the hydrogen bonded water cages in this ice like crystal will have a gas component. Either it will be CO2 or hydrogen or any other gas which is there in the feed gas. So typically when you have a mixture of CO2 and hydrogen, CO2 preferably goes into these solid hydrate phases. So once you form hydrate between water and gas, you have a solid phase which is enriched in CO2, and you have a gas phase which is depleted in CO2. So you basically, where you start, typically if you start at 15% CO2 and remaining nitrogen, you may need multiple stages. But if you start at 50-50, you need probably one stage to basically capture the CO2 up to 80 to 90% of CO2. Coming back to the energy penalty, if you see the membrane process has an energy penalty of around 50% of total energy produced. So suppose you have a power plant of 500 megawatt, 50% of that would basically just go in capturing the CO2 coming out from that 500 megawatt power.
Dr. Kumar, your slides are not moving.
It's shared, I guess. Yeah, it's shared.
Can you unshare and share again? And yeah.
No,
Go to the full
you have to enable editing first, and after that you put full screen, and the slide will come on just as a slideshow.
Maybe I'll just, because here in my screen,
yeah,
okay, I will just redo it.
Mm-hmm.
Okay. Sorry. Is it visible now?
Yeah, thank you.
Okay. Did you really hear anything or saw my slides before?
Yeah, you were no problem, but the slides were just staying on the first one. There was some...
Oh, okay. Okay. Now, can you see my second slide? Is it moving now?
full screen.
Yeah, we can see the capture of CO2 from a mixture. Yes.
It's not moving. You can see the slide now. But it's not moving. I'm trying to move to the next slide.
Why don't you move?
Okay, next slide.
It works for us. For us, it's okay. We are seeing them coming.
Okay, so what I was trying to say that if you are using different processes of CO2 capture, if you are talking about membrane process, your energy penalty is around 50% of total energy which you produce. And if you are talking about hydrate process, which comes around 20% energy penalty. Now, amine process, the capture cost is much lower, so the energy penalty is much lower in this particular case. But if you include the regeneration cost, then you see that total energy penalty is much higher in the case of amine process. Now, hydrate process being a physical adsorption based process, there is almost no regeneration cost because you can go to a lower pressure and CO2 will be just released by dissociation. Coming to the capture capacity of hydrate based process, so you see here there are other physical solvent, Purisol, Rectisol, and other mature processes. You see the CO2 capture capacity is quite low compared to the capture capacity which you see in hydrate form, which is quite high theoretically as well as experimentally. This number has already been achieved. So if you talk about the capture capacity of CO2 in hydrate process, it's as high as a chemical based absorption process. The only challenge over here is the kinetics of the process, and this is what we typically improve in our lab and the research which we do typically is to enhance the kinetics of hydrate growth. So now if you talk about the chemistry of it, you see that hydrates are formed in different structures. In the lab, you can synthesize a structure 1, a structure 2, and a structure H. These cages are hydrogen bonded cages where you will have a guest molecule which is encapsulated inside. So physically, you see it looks very much like ice. But at molecular level, you see there are two different cages in structure 1. You have a small cage and you have a large cage. There are 46 water molecules, 2 small cage, and 6 large cage in structure 1 hydrate. So a molecule like methane or CO2 is of such a size that it goes into the large cages as well as a small cage. So basically from water gas CO2 mixture, which is in order of 10 to the minus 3, you are going into a composition which is just 0.3. So that basically improves the capture capacity or enhances the capture capacity of water by 3 order of magnitude. If you have a molecule which is slightly bigger in size, say for example propane, it does not like to form a structure 1 hydrate because the molecule size is much bigger than the cage size. So it likes to form a structure 2 hydrate where you have slightly bigger cage. You see this is the cage of 12 pentagons and 2 hexagons, whereas in a structure 2 the large cage is 12 pentagon and 4 hexagons. So basically the size of the cage is slightly bigger when you form a structure 2 hydrate. And if you have a larger molecule, say for example cyclopentane or something similar, then you form a structure H hydrate where you have even larger cage which is 12 pentagon and 8 hexagons. So depending upon what is the gas mixture you have, you will be able to form different structures, and based on that you might be able to separate the gas mixtures which you have basically utilized in the process over here. So instead of CO2 and hydrogen, if you have CO2 and methane, you will have to probably form a structure H where you will use an additional molecule which will plug the largest cage, and CO2 does not like to go into the small cage and the medium cage of a structure H. So only methane will go into these cages, and you will get a mixture from a mixture. I don't know why this. Yeah, from a mixture of CO2 and methane. CO2 will only remain in the gas phase and methane will go into the hydrate phase. So that's the way you will be able to basically separate this gas mixture. So if you look into how the hydrate typically forms in lab, you have a gas which is CO2, you have liquid water, and then you just bring these two in contact with each other, and very soon you will see this interface starts getting converted into solid hydrate, and within a few minutes you see most of your water will get converted into hydrate, which looks very similar to ice-like crystals. We have used different additives to enhance this kinetics of hydrate growth. And if you see here, you will see the entire water gets converted into hydrate within a very fraction of a minute or in few minutes time. So that basically ensures that whatever gas you have it gets converted into hydrate, and the hydrates consist of one of the gas in the mixture, and the other gas gets enriched in the gaseous phase. So being a process which has multiple components, you have a gas, you have water. If you are dealing with multiple gases, you have multiple gases and water. And then you are also having multiple phases. You have gaseous phase, you have liquid water phase, and you have solid phase, which water gets converted into hydrate. So you have multiple phases and multiple components, and this is why it becomes very challenging to enhance the kinetics of this particular process. And this is where the reactor design comes into picture. The reactor design, we have looked into different reactor designs, and you see here a reactor design which has copper packing. So exothermic reaction of hydrate formation typically works quite well when you have copper packing, which is efficient in heat transfer in a better way. And then we use certain additives to enhance the hydrate growth kinetics. So in absence of additive, you see the growth kinetics is much slower, whereas in presence of these additives, you see the hydrate growth kinetics significantly improves. And with even less than half an hour, you will be able to convert most of your water into hydrate phase. And the amount is roughly 30 grams CO2 per gram of water. So basically the storage capacity is roughly 38%. This is much higher than any other storage capacity which you will get from any other physical solvent. So in this process, if you have 17% CO2, by this process, you need 3 different stages. If you have 50% CO2, you need 2 stages. And if your gas mixture is 70% CO2 and remaining hydrogen or nitrogen, you need only 1 stage for separation of CO2 into pure component. And the separation factor is, you see here, is around 36 for CO2 and nitrogen and around 98 for CO2 and hydrogen. What basically this means that there are CO2 and hydrogen mixture, it's 98 times more favorable for CO2 to go into the hydrate phase compared to hydrogen. So you get very high separation factor. If you look into the process, it's very simple. This is a reactor which has different multiple beds over here. You see these beds, which is copper packed beds. There will be copper and water, which will be interacting with the gases. You can supply a gas mixture from here. It would interact through this bed. The water will get converted into hydrate by incorporating one of the gas from the mixture. And then the gas which is coming out from here is pure gas. So you can basically continuously convert a gaseous mixture into a pure gas system. And this is the hydrates which actually forms on top of this copper bed. You see there is copper bed over here, and the heat transfer is much higher. And within fraction of minute, you will be able to convert your water into hydrate, where one of the gas is getting captured. So now what we have done is that we have captured the CO2. We saw how we can capture the CO2 from point source. Now the next step is to basically sequester the CO2. And this is where we basically again rely on hydrate formation to capture the CO2 as solid CO2 hydrate. So under the one of the challenge when we talk about CO2 sequestration is that we don't have many resources where we can sequester huge amount of CO2 which gets produced every day. Millions of tons of CO2 is getting produced every day, and you need significantly large resource where you can basically sequester this CO2. And under the seabed, we have huge amount of resources for capturing CO2. We are talking about 200 to 300 meters below the seabed. So we are not talking about the water. This is the seabed. So we are not talking about the water over here. We are talking about this region, which is basically predominantly sand and clay, and water, which is basically present inside the pores. So the idea is that if you see this particular blue curve over here, below this blue curve, hydrate will form. Above this blue curve, hydrate will not form. Above this blue curve, the pressure is low enough for hydrate not to form actually. Below this blue curve, because there is higher depth of water, so you have a better hydrostatic head. So hydrates will form. But we are not targeting this particular region, because here if you form, hydrate may form over here, but then there will be always a chance of hydrate dissociating because of water currents, and the CO2 will go and dissolve into the ocean, and that is going to increase the acidity of seawater. So we don't target this area over here, even though hydrate may form over there. We target this area. We take into account the geothermal gradient. So this particular area you see here is this area between around 1200 to 1300 meters below the seabed, below the sea surface. So this is around 300 meter area where we can form hydrate. And there are plenty of area where millions and tons of hydrate can be basically sequestered under the seabed. And we already know methane hydrate exists under the seabed for millions of years. And we know that at low temperature and high pressure condition, which is present over here, If methane hydrate was stable for millions of years, whatever CO2 hydrate we form will remain stable for next millions of years. So this is the idea which we try to implement in the lab. You see under the seabed, you have methane hydrate, which are stable for millions of years. The other option is that if you don't have resource, those places where you have no hydrate, you can even sequester CO2 in places where you have methane hydrate. One advantage you get by this process is that every mole of CO2 which you sequester in methane hydrate zone, you get equivalent mole of methane out of it, and this could be a sustainable process. So every methane molecule is produced from this process is burned to produce energy, and the CO2 which gets produced will be sequestered back into the process. So it could be a sustainable path. So we also do this research, and we identify the kinetics and the stability conditions by which you would be able to basically sequester CO2 under those conditions. So this is one of the small pilot plant which we have. I'll just show you what exactly it consists of. So this is our CO2 reservoir. From here, we basically supply the CO2 either in gaseous form or supercritical form or in liquid form. There is a heat exchanger which basically converts the CO2 into different phases. And then you can also have a small hopper where you can basically add certain additives to enhance the hydrate formation kinetics. And this goes inside this reactor, which basically simulates the conditions which exist under the seabed. That is 150 to 200 bar and temperature of around 5 degrees centigrade. So this is one injection well. And then we have two production well also to basically study the dissociation kinetics. So we try to understand the stability of these hydrates which has formed under the seabed. Suppose if there is 2 degrees or 3 degree rise in the temperature of seawater, whether this CO2 would dissociate or not. So that kind of a study we try to do. So this horizontal production well or a vertical production well would allow us to basically dissociate this hydrate and basically release the CO2 and water. Water comes over here in gas liquid separator, and the CO2 which gets produced from this is collected over here, and we can know the kinetics by which hydrate basically could be dissociated. So here, by doing this study, we know the rate at which CO2 could be sequestered, and doing this study, we know rate at which CO2 would be dissociated if the temperature of the seabed rises by say 2 degrees or 5 degrees, depending upon whatever we do in this particular study. So this is the reactor setup which we have in our lab. It's a part of the setup which is shown over here. This is the reactor you see. This is the gas liquid separator. This is the gas reservoir where all the gas gets collected up after the CO2 is dissociated. We put a cylinder of CO2 over here, which is put over a balance. This is a flange you see, which basically connects these two. So this is all automated system. We basically fill this reactor, which has 2 injection well and a horizontal well by sand and clay. In this particular case, you see it's all sand. And then we basically simulate the conditions which exist under the seabed, 200 meters below the seabed. And this injection well, which you see over here, you see these are injection and production wells. So it basically has perforations, and these perforations are covered by a stainless steel mesh to basically stop the sand going inside the production or injection well. So through this setup, you can get this kind of data where you have CO2 dissolving in the water first, and then once hydrate starts forming, you see there is a real-time kinetics by which you can basically capture the kinetics of CO2 uptake or CO2 fixation under the seabed. And if you have methane hydrate and you are exposing CO2 to methane hydrate, you can do similar studies by doing looking into the composition. So here you see you had pure methane hydrate, you expose pure methane hydrate with CO2, and over a period of time in 700 hours, you see you have 58% methane and 42% CO2. So you have recovered 1.4 moles of CO2 methane in this particular process. An equivalent amount of CO2 has already been sequestered in this particular process. So this is overall design. You see over here that you can basically inject the CO2 in similar ways by which we have basically learned to exploit cell. So you can have horizontal wells where you can basically do small fractures and then CO2 can be injected, and this entire section gets converted into solid hydrate. This is not exposed. This portion is not exposed to seabed, so you don't expect this to dissociate without even if it comes in contact with because it never comes in contact with seawater. So this is the group which we have multiple. So the project scientists or PhD students are there in this group. Any interaction can be done through the email ID which is provided over here.
Thank you very much, Professor Rajneesh. I'd like to ask some of our attendees if they have some questions to ask, and if they could raise their hand. We are running quite a little late with something like 25 minutes, so please some short questions.
I have a question. Can I go?
Yes, please, Professor.
Rajesh, very good talk.
Thanks.
You focused on carbon dioxide sequestration in the ocean. You also said that cement production does create a huge amount of carbon dioxide, including the limestone. If that can be captured, that can be actually put into a concrete, which doesn't have to go, and which can be actually done in a relatively short time, wouldn't require the kind of infrastructure that you. What do you see the possibility of that, and how soon can we do that?
Yeah, this is a very interesting question. And see, CO2 sequestration can be done in multiple ways. Under the seabed, obviously, is one of the options. And what you are talking about, sequestering it in cement. So this is certainly
concrete.
Yeah, cement, either mortar or in concrete. So it can be done in both ways. Prefab concretes and cement mortars can be utilized, because these places are supposed to be from the point source. So wherever you're doing this prefab construction, we can basically certainly sequester CO2 from the point sources in prefab construction. Slabs and all.
Do you think we can do that in about a year to 2 years time frame?
This kind of study can be done in lab in a year time frame, but implementing it would require some infrastructure development, because CO2 pipelines and CO2 source has to be closer to where the prefabs are being done. So those kind of study has to be done, like how far you can be from the location where the concrete prefabs are being manufactured.
I have one follow-up question to that. So can this hydrate be a route for transportation rather than sequestration?
Yeah. So that's what I have not talked about it today. So hydrate can also be utilized for transportation. This is why initially I talked about that we do work on transportation of CO2 also, again through hydrate route, because since the storage capacity is quite huge, you can utilize this for transportation of CO2 as well.
So would you say, in terms of using compressed CO2 as transport versus hydrate route, what will be the volumetric?
The only challenge I see here is that you will need two pipelines. One for the dissociated water to come back, because the water is a very precious commodity. So it becomes a challenge like that, say, the Dilbit challenge. You have this diluted bitumen, no? So you need two pipelines, one for the solvent and one for the. So this is the challenge which we will also face over here.
Thank you.
Okay, thank you very much. Thank you for this very good interaction and presentation. Thanks again.
Thanks.
I'd like to invite now Mrs. Camille Beignet from Total Energy to give us her presentation. So Camille, over to you.
Yes. Can you see my screen?
Yes.
Perfect. So hello everyone, I'm Camille Beignet and I am a research engineer in Total Energies in the solar R&D program. So right now we're going to go back to solar subject, and I'm going to present you the activity that we have inside this solar program. After I give you a few elements of context about Total Energies.
Hi Camille, we can't hear you too well. Could you be a little louder, come closer to the mic?
Is it better like this?
Yes, this is better.
Okay, I will try to speak closer to the computer. So a few elements of context about Total Energies. So Total Energies is transforming itself into a multi-energy company to better meet society needs. So more energy because of the growing demand and growing populations, but at the same time we need to reduce our carbon emissions. And Total Energies has strong ambitions on becoming carbon neutral by 2050. So we are acting a lot in this area. So for this, we are evolving our energy mix by reducing the oil parts and increasing the biofuel, the natural gas, and the renewable electricity part, mostly with solar and wind production. And to support this strategy of increasing the energy production and reducing the greenhouse gas emissions, we have 4 pillars that we have based ourselves on. So focusing on natural gas, biogas, and hydrogen. Secondly, is to produce renewable electricity, mostly with solar and wind. The third one is the decarbonization of our assets. And the last one, we saw it a little bit in the previous presentation, that it's implementing capture and storage of CO2 via our carbon sinks. So today I'm gonna mostly speak about the electricity part. So it's been several years that TotalEnergies has been in this area. So it started in 2011 with the acquisition of SunPower, which is a PV module manufacturer in the US. And a few years later, the branch GRP, which stands for Gas, Renewable, and Power, was created. And then several companies joined TotalEnergies, such as, for example, SAP, a battery company, or energy provider company like Lamperis in Belgium, or Total Spring in France, and some other companies that generate and operate PV plants, like Total Eren, Total Solar, and Quadrant, which we are closely working with inside the R&D. And so to achieve an energy mix dominated by renewables, there are 3 challenges that we are closely looking at within our R&D programs. The first one is increase the renewable energy production. So this is with our solar and wind research programs. The second one is to reduce the intermittencies caused by renewables by operating hybrid systems with renewable source, non-renewable source, and storage systems together. And the last one is to smoothen the demand curve. So you know that the energy demand is not the same throughout the day, throughout the seasons, and you need to smoothen this demand. And so we are looking also into what we call energy management system, to better know when we use the energy, when we store, when we deliver into the grid, and to smoothen this demand. I'm going to go now more into detail of the solar program. So just a few words about the R&D in TotalEnergies. So we are looking at a lot of subjects, but today I'm going to focus on solar, which is located in the power R&D line that you see on the left. And so we are closely working with the wind program, hybrid and storage program, distributed energy resources program. And we are supported by a numerical platform that helps us for modelization and simulation, and an experimental platform for our experiments in the laboratories. So now I'm going to go talking more for the solar R&D program and what we do. So I was mentioning earlier that a lot of companies in the renewable sector join TotalEnergies, and our role as R&D is to support these companies into achieving their objectives. And their objectives are to install more PV capacity in the world, to improve the assets cost and efficiency. And the last one is to scale up a new technology through pilots and demonstrators. So our program is structured to help them to achieve these objectives. And so for this, the solar R&D has 4 main focus areas. The first one is, how do we better assess a site? How do we identify the site? And then how do we forecast what is the potential of the solar production on this specific site? So that's one of our first topics. The second one is to reduce operation and maintenance costs. Sorry. So that's by the choice of the material we make in terms of modules, but also inverters and structures. So we do qualification and also reliability testing. We are also looking at different maintenance strategies, for example, cleaning robots, and also different inspection techniques to better assess what is the state of a PV plant and identify defects and be able to do some preventive maintenance action. A new topic that we are looking at also is new photovoltaic usage, especially agrivoltaics and floating PV, to extend the possibilities in terms of land where we can install PV. And the last topic is AI tools for photovoltaic, so artificial intelligence tools that allows to better manage the assets and predict the production of the PV plants in the next few hours or few weeks to do better decision in terms of energy utilization, but also detect some defects or underperformance and trigger some predictive maintenance operations on the PV plant. So that's the 4 main focus areas. So to do this, we are located in different places. Our main one you can see next to Paris. It's our laboratory in IPVF that was presented before by Jean-François Guillemot. So I will not present IPVF any further, but we have one laboratory located there where most of our team is. And here we mostly do qualification of the module or extended aging tests indoor in our facilities. Another location that we have is next to Lyon in France. And here it's mostly dedicated to hybrid systems. So PV linked with the storage systems and non-intermittent source. And all of this managed by an energy management system to develop this energy management system. In the south of France, we also have some demonstrators that are going to be ready soon on agri-PV and also floating PV. And then outside France, we have also part of our team located in Qatar, where we have a test site in desert environment where we do a lot of testing. And we also have some people located in California, where SunPower has a R&D center. But this part is mostly on SunPower side and looking at PV cell architecture. So a few words about our main location. So in IPVF, so we have our own laboratories there. So we have a pilot scale solar cells and module processing line, but most of our activities relies on the indoor and outdoor platform for PV qualification. So we have a lot of equipment in the lab to do like the IEC tests for reliability on PV modules, and also some failure analysis on some panels that we can receive from the field, for example, and the test site on the rooftop where we can install some equipment and assess the performance. And not far, there is another team that is a numerical team that is working on modeling and simulation that is helping us on our digital project. So we have had, as I said, private labs, but in IPVF, we are also contributing on common research projects with IPVF that Jean-François Guillemot presented earlier. And we are mostly contributing on the reliability work on peroxide for PV cells in general, and the life cycle analysis of PV components. So to present you the team, so our program manager is Gilles Poulin, and he decided to split this R&D program into 4 main teams. The first one on the left is the one more close to digital application. like how we're gonna predict solar potential of the site, how we're gonna identify a site geographically, which site could be interesting to look at, and yeah, simulation of PV plants and how do we optimize the layout of the PV plant. So later on, I'm gonna show a few examples of what they developed. The second part is on component reliability and life cycle analysis. So historically, we have a lot of activities on PV module qualification and reliability testing. So a lot of aging tests to qualify PV modules, and also some failure analysis that we can do on some PV modules that show defect in the field to understand what is the degradation mechanism that happened and how do we prevent this from happening again. And here the goal is also to look at more detail in the mechanism, the degradation mechanism of the PV cells. How can we model that, predict it, and how does it evolve depending on the climates? All these kind of things. And here, as I mentioned earlier, we also take part in the common research program with IPVF, especially on the reliability of peroxide. So what are the tests we can use for assessing peroxide reliability, which are different than the one we use for silicon? And how does the peroxide evolve? And we start to have some outdoor exposure with some samples that IPVF is preparing. And then the next one is our team on operation and maintenance and performance. So here we gather all our experiments in outdoor demonstrators and test sites. So we have sites in different areas in the world, which allow us to look at different climates and install different technologies and see how they behave in the field. But also looking at different maintenance solutions. I was saying earlier, tuning robots. And also, how do we monitor a test site via sensors, but also some algorithms to detect if we have some underperformance or defects happening and how to spot them early in order to do predictive maintenance action. And finally, the last topic is sustainable PV. So here it's a very new topic and is mostly looking at agrivoltaic floating PV. When I say agrivoltaic, it's not only the PV panels and the PV structure that we're gonna use on an agrivoltaic project, but also what is the synergy with the crops, with the plants that we are gonna grow alongside the PV. And how do we optimize these two yields, the PV yield and the crop yield, which is also very important to take into account. And so alongside this, the aspect of eco-design of PV panels, recycling, and also the subject that are going to come soon of repowering of old PV plants are also some aspects that are going to be looked in this area. So I can detail a bit more with a few of our flagship projects. So I'm going to talk first about the outdoor demonstrator that we have, because we can do a lot with these sites. I will take the example of the carport that we have in France, where we installed the bifacial PV panels, where we were actually looking at the performance depending on the albedo, depending on the type of ground that you have below. Is it concrete? Is it paint? Do we have a car that is parked below the PV panel? Do we have nothing? And how does this influence the production of the PV panels? So that's something we are monitoring now and we are looking at regularly. We can also install panels in different environments. I will show you just later, just a bit after, a map of our test site, but we can have some panels in a desert environment, temperate environment, or tropical environment. to see how differently they can behave with different environmental conditions. You can see on the picture on the upper right some cleaning robots. So we did like a benchmark of different possibilities for cleaning solutions because the soiling issue can be important, especially in desert and very dusty environment. So that's also things we are looking at. And the last topic is I was mentioning the monitoring of the PV plant and how do we inspect the PV plant to see if we have defects. So we are also looking at innovative way to inspect, for example, via drones with the infrared camera or even doing electroluminescence by drones that can give us different information. So we are looking at these different possibilities, different technologies that can help us to monitor better and anticipate issues that can happen in the field. Yes. So this is the map of our different sites. So as I was mentioning, we have 3 in France. So the rooftop of the IPDF, an agri-PV site in Pomot, and a carport in Vichy. And then we have where our team is located in Qatar. We have a test site in desert environment. We can also have some single axis tracking, not only a fixed mounting structure. And we also have access to 2 locations in tropical environments in Martinique and New Caledonia, where some affiliates have a PV plant and we have a dedicated area to install products. So just a remark, so the test site that we have give very valuable information to us. And if it would be of interest to you to work together on a test site in India, that's something we would be interested also to discuss. So if you have any needs or ideas, it's something we can discuss later on. And last, I can show you 2 examples of the digital project that we carried out. So the first one is called the Solar Mapper. It's something that has been developed with Google, and it's actually a tool that allows people to know the solar potential of their house. So it basically look at satellite imaging that are provided by Google. And with this, we can calculate the surface of the roof available, which is the orientation of the rooftop, and what could be the potential in terms of solar production. So this tool right now, it's in pilot phase and it's being used by 2 of our affiliates in France and Belgium to propose some options to customers for residential solar applications. What could they expect with solar installation? And the last project, it's also a tool that has been developed by our teams, but it's mostly for the use of the people who design the PV plants. It's a tool that is similar to PVSys, but allows to tackle more complex situations. So you can basically model your PV plants and see what could be the solar production, but you can do more complex situations with bifacial, for example, different albedo situation and so on. So we gain a lot of time in terms of the optimization of the PV plant by using this tool. And we also have more accurate predictions when we are considering more complex layouts, especially with bifacials and agri-PV as well. That's all I have for now. But if you have questions, I will be more than happy to answer.
Thank you, Camille, for that presentation. Want to first open it up to the audience that have joined us here if they have any questions. If not, we've received a few. One question that we had was on what kind of work or progress you've made on recycling of these panels. Has Total been working on it? What is the progress that we're seeing?
So the recycling is something that we added really recently in our program. We are not looking really at the process right now, but we are interested in contributing in some common, for example, European project on that. The goal for us is more to understand what are the recycling routes that are more interesting and have less impact to really make better choices also in terms of module procurement, because the end of life of a PV plant is something that we have to take into account, and the choices depends also on the recycling possibilities at the end.
Sure. And one more question, I think, from some of our Indian participants is what kind of work is Total Energies looking at doing at India specifically? Is there sort of an area of focus, areas that are currently under researched in the Indian sort of market scenario?
So it's really open, but my colleague who works on agrivoltaics, for example, he told me would be very interested if there are some agrivoltaics projects open, or for example, projects where you have PV but coupled with other things, for example, PV with maybe water pumping for watering crops or desalination of some water coupled with PV. All of these kind of complex or coupled uses we are interested to look at. And yeah, we are open for discussion.
Sure. Thank you. I think that's all the questions, and we're also running behind on the schedule. So thank you again, Camille, for your presentation, and we look forward to more work from Total and India partnerships.
Thank you.
Thank you. You can stop sharing your screen.
Yes, actually, I lost the.
Okay, great. For our next presentation, I'd like to invite Mukundan Max Narasimhan from Play Solar to share with us his insights of his journey at Play Solar. Over to you, Max.
Thank you. Are you able to hear me? And
yes.
Are you seeing my slides?
Yes, if you could only make it full screen.
Yeah, it is already in full screen. Okay, let me see if I can. Yeah, I'll have to share entire desktop. Maybe that'll work. 1 second. Is this better?
Yes, please.
Okay. Thank you very much, IITM and IFI, for organizing this sustainable energy workshop, and glad to be a part of it. My name is Mukundan Max Narasimhan, and I represent two companies, one in India, Play Solar, which has been around for 6 years, and Gridchill, which is a newer entity that we just formed in Singapore for raising funds, etc. Right? The topic is titled New Energy Paradigm, but it will go through some of the areas that Camille earlier mentioned out of Total. So these are some of the areas that we are working in, similar thought process as Total, but as a startup. So our perspectives are somewhat different. So Gridchill Group is the parent entity is in Singapore, and we have Gridchill India as well, which was established in July of 2019. And Play Solar India is also working from the last 6 years in India. So as you know, even with 300,000 plus years of human evolution, we're stuck with archaic energy generation and distribution systems. You can see that 25 to almost 40% of discoms, basically the costs are avoidable, the operational costs, OPEX costs. Primary challenges are the supply demand management and high cost of peak power. Solar has come and evolved, but it still has its own set of issues, like 7 to 15% dusting losses. India is blessed with, for example, a lot of sun and a lot more dust. So that problem is still prevalent in countries in Southeast Asia and Africa, in the Middle East, for example, etc. The losses could be much higher, even though the simulated losses, you can never simulate dusting that accurately, right? So this is an area where we're focusing on. Then in addition to that, depending on the options available locally, we have very limited options to use the energy that's generated using solar on location, or store it in batteries, or sell to grid at a very low price, leading to almost 25 to 30% energy wastage, depending on where you are and what kind of PPA rates you enjoy, right? So, we as a company work on several of these areas, what I call as peripheral and integral innovation. A peripheral to the core, like the inverter or the panel or the battery, but integral to the overall progress because of additional energy efficiency you can gain in the generation side. And we'll also talk a little bit about how energy efficiency contributions can be made in the how the consumption is of energy is being done, right? So one is similar to the Google Sunroof project that Camille mentioned. We are integrating some solutions for instant proposal generation. So basically time used to generate a proposal for, let's say, a residential rooftop project, and also social media integration, right? So this is one area. And then we have our own, basically drone survey integration, where we automatically survey the plants either during, before construction, or during construction, or post construction, using infrared or EL cameras that permit automatic package integration and automatic layout for the panels, right? And in addition to that, then we have a digital QA process, which is basically a project management platform for specifically designed for solar, from order receipt all the way up till commercialization, complete and commissioning, and the project being up and running. And there is a lot of AI optimization in terms of schedule optimization that can be done to accelerate the rate at which these installations can happen, right? And how the approvals can happen, right? Then we have a couple of very innovative solutions on AI-powered remote monitoring and control platform, and an O&M scheduler, which automatically schedules all the O&M activities using AI algorithms. And also we have an automated cleaning solution, which we will talk about a little bit in the next slides. And we also have Home Solve, which is a demand response solution, which we are basically empowering for clients, giving them breaker level controls and energy optimization at the local level. And in addition to that, we have started a small initiative with working with some of our utility clients on blockchain-based peer-to-peer energy trading platform. Yeah, on the module soiling, you can see these areas. The blue areas is where extremely high soiling losses exist in the southern side of US, for example, southern and western side. Africa, of course, India, and several other Southeast Asia countries, and Australia. Middle East, of course, is a big area where dusting is a big problem. With utility and commercial scale market is over 670 gigawatts already. Now with that in place, the soiling losses are still, even though the PV-SYS simulation may say 7 to 15%, 2 to 3%, the actuals could end up being as high as 7 to 15%. Manual cleaning is expensive and needs to be done at odd hours, because you don't want to clean the panels during the day because it's hot, and you don't want to mix water and temperature at the same time. So manual cleaning leads to unfortunate damages, as well as poorly executed cleaning, and this could be 25 to 35, even higher percentage, depending on where you are, of costs and how often you clean, right? And extremely high water consumption, 1.3 liters or even higher per liter per panel per clean cycle, which is again an environmental concern. Water is a very premium commodity that you cannot use for this kind of large scale installations. So cleaning it done also because of that, cleaning is done at an arbitrary schedule based on cost, as well as whenever somebody puts a 1 month clean every month. Let's say Europe is cleaning is done every 3 months or 6 months, depending on how the dusting level is. India is done every 2 weeks or a month. And there are existing robotic solutions, I think, which Camille a little bit touched on. Those actually offer, it's the only moving part in a very stationary solution. They may not offer the reliability and consistent boost of energy performance because they are not doing what an ideal cleaning solution would do, which is similar to simulating a rain. So what we have done is 3 different solutions in this area. One is CleanSolve, which is AI-powered solar washing, which we developed, co-developed with GE, and we have secured the IP for that as well. And we are consistently seeing on commercial rooftop solutions anywhere between 7 to 12%. We are working on ground mount installs where we're adding on this solution as well, where we're seeing some significant improvement. And because we are recycling the water as well, and we are seeing significant savings in water, so there's no water wastage, and the robotic issues go away, right? Then we have an AI-powered solution that determines which panels get more dirty and when that happens. And using that trigger, we are able to clean those specific panels that get dirty more and more often. So this is an automated self-learning edge algorithm that we have developed internally, and this can scale and can be deployed in high speed, and we are starting to do some early installs in the Middle East for this solution, right? As I said, in the energy automations area, where how the energy is being utilized, we are also working on some solutions integrating with blockchain. I'll talk about it more in the next slides, what some of the applications could be. And we have also filed some as a PCT application. This could have a potential to save almost 20 to 30% in terms of OPEX and energy savings. So as far as the approach to market for the earlier solution that I mentioned, the cleaning and O&M automation solution, the right approach we see is integrating in a one platform where you have automated cleaning, the predictive analytics, and the drone-based health analytics using EL and IR thermography, and create a digital O&M platform, which makes the overall cost of O&M at much lower, and early detection of defects are not too late, right? So this has a potential to understand the actual risk in the asset and mitigate it, which could, for example, reduce the risk premium in solar. Right now, the equity is valued at 30% and the debt is at 70%. That could really come down to 10% equity and 90% debt if the risk is taken by a proper solar insurance cover. So this is some areas that we are working on. And as I was telling you, this is the digital QA process that you run through each and every area of how the solar is being built as it's being built, and it's like a digital clone of the solar asset where you have all the data digitally available, and certain optimizations in the process can be done using AI as well to optimize on schedule or performance. This is the peer-to-peer energy trading platform that is now we are looking at implementing with certain customers in Malaysia, and also starting to do some early trials in the US, where you combine energy automation with peer-to-peer trading. I think peer-to-peer energy trading, pure play blockchain companies have tried, but they don't understand the energy domain that well. And with our background, we are able to integrate both the optimization of how the energy is being utilized in-house so that the trading is also optimal. So this is an area where we are working on, and some of the applications are, I'll jump into the next slide because we're running out of time. So we have 4 different applications that we are working with. One is REC trading, where we integrate the AI and blockchain ready solution, whereas you can basically eliminate the middleman, which is a certifying authority for certifying a trade. And since it's IoT enabled with smart meters, you can do very accurate billing on what the actual REC certificate value could be and trading of that, right? So second is a smart contract for chiller as a service. Typically, a chiller goes on a rooftop as a product sale, and the end user has no idea how to maintain it, or it's not properly maintained. Take a country like Malaysia, when the relative humidity of the country of the location changes by 2 or 3%, the entire AC or chiller units consumption of electricity goes up drastically, leading to immediate turning on of peaker power plants. These can be avoided if the smart contracts are in place for the chiller manufacturer to also maintain it, and if they don't maintain, they're penalized using the smart contract validated by a bankable authority like the utility of Malaysia, right? So additional area is smart socket solutions for EV charging, where the utility can deploy these sockets wherever they want, let's say connected to individuals in every street corner, and the billing automatically happens using peer-to-peer trading, where the person who wants to charge it charges it at the socket, and the bill reduction happens at the host's place, and the amount is credited to the utility at the appropriate prices. So the last one is basically demand response solution using distributed battery. Instead of turning on peaker power plants, if you distribute with a higher capex initially, many batteries at commercial sites, where locally those surges of use of power can be mitigated using those batteries, you can avoid high cost of peak demand, right? So these are some of the solutions. We have been recognized in the Indian market with a few awards, but the best award that we have received is with all of our clients, and the repeat orders that we seem to get from them. Thank you very much for your time.
Thank you very much, Mukundan, Muksa. Very interesting, and very happy after having heard some previous presentation about solars to have somebody focusing on dust. I've been living in India for 15 months, and wherever it comes from dry area or from construction site or from demolition site in the city, I've seen a lot of dust sometimes. So very interesting. Have you got, first question, have you got an idea on how has this cleaning and monitoring has got already been measured, the impact on the life extension of the solar panels with a health check you're doing with the drone? Yeah.
So I think we are at a point where with the drone, we are able to analyze the type of defects automatically and categorize them. Right. That way, we know if there's a junction box leakage, diode issues at the back of the panel, or any connection, loose connects, or certain subarrays that are not working, etc. We're able to do that, and then categorize them automatically, so that the guy on the field needs to know exactly what to do at the exact location, so that the time is minimized and labor costs are saved, etc. In terms of also warranty claims can be had, because we are also doing ID mapping based on location of the panels. So each panel, what are the issues are, we can actually log it automatically, and that way warranty is honored by the module manufacturer. So this is an area that is of interest. In terms of life extension, I think the key areas are thermal management is one, and proper cleaning, and the 0.5% degradation that happens on a yearly basis. It's a physical phenomenon that cannot be. I don't think it can be dealt with. But LID is an area where proper, the junction characteristics can be done properly at the manufacturing level to improve the LID. Yeah.
Okay. Thank you for the details reply. Have we got another question from the panel? I can maybe add one that I had received before. We have seen, notably the previous presentation from Camille, some BIFA shows panels which were verticals. Would that be a limit for your drone to be able to come and do this health check because of the angle for vision?
No issues at all. I think all types of defects on the panel level we are able to detect, and with more than 95% accuracy.
Even on the vertical panel?
Yeah, on the vertical panel, it's basically you need to mount the camera at a different angle, and you can do the same analysis.
Okay, good. Thank you very much.
Thank you.
And if we don't have other questions, I'd like to invite Mr. Bruno Presta from EDF, Electricity of France, to share with us his presentation. Bruno?
Yes, good morning, everyone. Bruno speaking from EDF Research and Development. I share my screen. Looks like I cannot do it for the moment. You should probably.
I'm going to ask the administrator. Tejas, please, can you?
You should
give the go to Bruno.
Mox, I think we're still seeing Mox's screen.
Yes.
Can you stop sharing?
No, I cannot share my screen. It looks like it's blocked. Somebody else is sharing his screen.
Trying to shut off, but I don't know how.
Mux, yeah, can you just stop sharing?
I'm trying to figure out how to do that because that option went away for me.
There should be an option.
There it is. Got it. I
Right.
think that should be good. Okay, sorry about that.
Make a try, Bruno.
All right.
Should be okay.
All right, that's it. I don't know if you see my screen. I hope so.
Yes, beautiful.
I'll try to put it in the. All right. If you're good with that, it should be okay, right?
You're not full screen.
I'm not full screen now for some reason.
Diaporama.
Diaporama. All right, here. All right, you got it.
It's a little slow. Yeah. Oops. Yes. Okay, it's good. Over to you.
Well, so again, so Bruno, Presta, EDF Research and Development. I'm with EDF R&D international activities, in charge of specifically collaboration with our 6 R&D centers abroad. And I am an expert in microgrids, and the focus of my talk today is fostering decarbonized microgrids. So the picture on the right doesn't show any microgrid, but we'll come to that afterwards. On this first slide, the message I would like to convey is that there's really a global trend to foster the development of decarbonized microgrids. So there are many applications, as you might know. There are many remote areas like villages or small or big islands. Sometimes it's for electrification, which means bringing electricity to some place where there's no electricity at the time being. It could be also ensuring an energy transition in those places, typically when there's electricity, it mostly comes from diesel gensets, with all the drawbacks you can guess in terms of cost and pollution and noise and some others. So there's really a trend to go for decarbonized microgrid in those areas. We have also what I call off-grid industrial sites, and that could be, as you see on the picture, like mines. They could be off-grid, means not connected to a grid because they are typically far from the rest of the power grid. But again, they would run on 100% diesel gensets for the time being. And we want to ensure, again, an energy transition, which means typically to integrate renewables. And also there are parts of small rural or even urban sometimes areas that's mostly seen on the picture on the bottom right that shows a village with apparently a lot of rooftop PV here. So we can assume that the village would be connected to the grid in a normal situation. But what happens in terms of when there's a grid outage? So instead of having a local blackout, indeed we would like to do it much better and ensure an energy supply even during the outage, or if there are some grid works, for instance. So we try to leverage the local energy resources, and in that case, there will be typically PV panels. So again, there's this global trend, and then energy transition is a very overarching goal, and we'll really rely on local and green distributed resources. I would say on the flip side, transitioning to what I call deep decarbonation brings also new challenges. There are many challenges regarding the power system flexibility. I will come back to it afterwards. Power system stability, frequency control, backup power. We need also very specific controls and communications systems. And we need to ensure level optimization, and we ultimately want to have this, to prove that it's economic in the long term. So there are many challenges. So there's nothing really simple in microgrids, and sometimes people would tend to say, okay, microgrid is a small system, it should be easier. No, it's not easier. It's not. Basically it encompasses the same challenges that you would find in a larger grid. But on the good side, on the positive aspect, we believe that the promotion of decarbonized electricity uses in microgrids could bring additional flexibility. So what I mean with that is that, as you guess, integrating renewables is a bit more complicated than integrating a power that you can control directly, like a genset. That's I would say obvious. But what you need, basically, whatever it's a small or large system to include renewables, is to make sure that we have an increased flexibility. And in this case, in the case of microgrids, we believe that we could have more productive uses using electricity. Here I name motors and drives, water pumps, for instance, some mills, some also commercial refrigeration. We've seen, for instance, in Indonesia, in a project, fish conservation. So fishermen would get fish from the sea, and they need to store the fish in large fridges, I would say. And those fridges that are really local could be, by the way, use decarbonized electricity, and also could be, I mean, at least to some extent, a way to provide some flexibility, because you can adjust the temperature and without hampering the freshness of the fish, and providing some flexibility. Same for motors and drives or water pumps. There is some flexibility that comes with these new electricity uses. There's indeed electric mobility that's coming also, that's coming basically everywhere, but that's coming also in microgrids. In a microgrid, we can consider 2, 3, 4 wheelers, like shown on the picture, like it could be small vehicles or mopeds. We can have light or heavy duty vehicles, even sometimes by the ocean to sea e-boats. And again, all these new mobility technologies would bring some additional flexibility. The third component that's kind of common in microgrids, it's about batteries. Basically, you'll find batteries in most microgrids, and they are made to provide flexibility, that's obvious. But my point is to say we don't need to rely only on batteries because these productive uses or electric mobility can provide additional flexibility. And it's really what we need to include more renewables in these microgrids. So it's really key to develop these new electricity uses and to be able to combine them in microgrids. I will illustrate what I say with showing two slides about, three slides, about what we call the Mazira microgrid. This is in Singapore. This is a microgrid demonstrator that we built a couple of years ago. It's been operational for 3 years. It's on a small island of Singapore in the south of the strait, facing Singapore a couple of miles south of the city, as shown on a small picture. It's a collaboration between a local university, EDF, and Enedis in France. And basically, the goal of this small microgrid, I'll show you a picture just afterwards, was to demonstrate that we could do an affordable microgrid, a sustainable microgrid, and a reliable and resilient microgrid. So we believe that these three attributes are really what we are looking for when developing decarbonized microgrid solutions. So it's actually this, you see the picture on the next slide. This microgrid is really what we call a pre-commercial one. So it's an R&D microgrid, obviously, but it's really fitted to, to be able to develop commercial microgrids based on this, I would say, similar design. So it's fitted to remote areas, again, villages, resorts, there could be small islands. It's scalable in terms of design, so it's a small one, the one we have in Singapore, but it could be expanded up to several megawatts, and with this, again, the same design and concept. It's an operational microgrid. I told you it's been operational for 3 years, and we really made a point on really leveraging EDF solutions for decarbonized energy supply usages and flexibility. So it's quite full of innovation also in terms of technologies. We have developed a specific energy management system. We have integrated bifacial PV. I'll show you that on the picture. We have also integrated an EV and V2G behind Coal-to-Grid, and some other innovative technologies and solutions. We also decided to go for a containerized microgrid because we believe this is what we will need when deploying at scale this solution across, again, some villages or countries. And last but not least, we try to stay in an overall low-cost approach, really trying to compress the cost and to make the best choices in terms of technologies. So this is how it looks like. So it's a small microgrid. It's rated 100 kilowatts in terms of generation capacity. What you see with the blue and white stripes on the bottom right is simply the bifacial PV panels. The blue stripes are the panels, and the white ones are reflectors to benefit from light coming, from these white stripes of metal would reflect, and the electrons would go, the light would go through to the other face of the panels, ensuring, roughly speaking, 15% in terms of power generation that we get with this technology. That's quite interesting. We have there's nobody living here. It's again, it's a demonstration project. So we have a load bank that's able to represent any kind of load, and so it's indeed extremely flexible. We have a small genset because, again, in most of the microgrids, there are gensets, so we want it to be in quite realistic conditions. So we have a genset, and indeed the goal is to I wouldn't say get rid fully, but to limit the use of the genset depending on the load curve. We have installed, it's not visible, but it's in the box, it's in the container. We have installed storage technologies, currently a lithium-ion battery that's, I would say, kind of conventional. And there's a plan to include a second life EV battery that's supposed to be a cheaper option, leveraging the batteries that are after, I don't know, like 7, 8, 10 years in a car would still be in quite good shape and be used for stationary applications. We have a weather forecast and we have as you see, there's a car. So here it's a Nissan Leaf, but it could be any other car. And there's a V2G charging station. So again, when we designed Mazera, we wanted to leverage these applications of electricity I mentioned. So we decided to put a car, and the car is really able to charge depending on the needs and depending on the PV production. And in some specific cases, the car is able to re-inject energy to the grid, like discharging the car battery. This is really the V2G concept. So as you can see, there are really 3 main flexible technologies, so flexible load, flexible storage, and again, a flexible load and storage with the car. So message is again, let's go for very flexible microgrids, and that's really a good way to include more renewables and to go for more decarbonation. I mentioned also, you see that on the bottom right, that we have developed a full, say, EMS or DERMS, distributed energy resources management system for microgrids and specific for these small configurations. So, so in essence, the takeaways are that deep microgrid decarbonation is feasible. We can even go to 100% decarbonized microgrids. When we want to go to 100% full-time means that it could be quite expensive. Economics could be challenging, and typically that would require a very large amount of batteries, or at least battery capacity. So oversizing the batteries. So it's technically feasible. That's why I say it's technically, it's economically speaking to be discussed. Again, load flexibility is really key. So new electricity uses really can provide additional flexibility, and this is what we need. So more flexibility means more renewables, means more decarbonation. And last word on the EMS, that's a key component, and going for deep microgrid decarbonation also require some specific EMS solutions to be able to not only to manage a generation, but also how electricity is used. So again, V2G typically are also controlling some part of the load, which is what we call demand response generator. So DMS could have or should have a broader scope, and this is not always what we find on the market. This is why we developed our own EMS solution to be able to really encapsulate both generation and load in the global optimization. So, and then as you might guess, EDF R&D has developed now quite good skill sets and innovative tools and solutions for the development of decarbonized microgrids in the world. So this Mazera microgrid is one example, but there are more operational and commercial microgrids. There's one picture on the bottom right that shows a French island in the west of France, here in what you call Brittany. And it's an island that's really transitioning, I would say, from 100% genset based to 100% renewables over time. It means it will take probably 15 years, something, to get to 100% decarbonized, but we'll make it. And that's it. Thank you very much.
Great. Thank you so much for the presentation. I want to open it up to the audience for any questions first. We've also received a few from our side.
Yes, some in the box.
Okay, so I'm going to go ahead and ask some of the questions. You mentioned some of the work that's being carried out on the EMS side. Is there some progress that you've made in terms of commercial deployments where the EMS has been used?
The thing is that when we designed this Mazera microgrid a couple of years ago, so this one, we initially tried to use an existing EMS solution, and it turned out that it was quite complicated. It was quite expensive, and it took us a lot of time to configure the EMS to make sure that it was in good and proper operational condition. So we spent too much time, and it was basically a bit or even too complicated. And we said, okay, this is not going to work if we want to go at scale and develop microgrids, I would say by dozens, or if you want to electrify a country, like for instance, in Africa, as you know, there are many countries where there's a big gap still in terms of electrification. So if you're not going to do one single or one-shot microgrid, if you want to go at scale, you need a very specific EMS solution. I would say kind of a plug-and-play solution that's really dedicated to microgrids. That's not complicated to be installed, not complicated to be configured, and that ensures also remote communications. And so we didn't find it, so that's why we developed it.
Sure. One last question in the interest of time. What was asked was, in terms of technology for storage, is there something that has made more progress than the other? I know you mentioned lithium-ion as well as redox flow batteries. What do you sort of see in terms of future for energy storage in these microgrid projects?
Well, as you know, there are many energy storage technologies and making progress, I would say, every day. To be clear, the lithium-ion battery technology remains quite, probably on the top of the range, because it's become the common technology, and so that's why also we try to include this technology. That's typically what we will find in commercial microgrids. EDF R&D in parallel is extensively working on storage technologies, trying to foresee what's coming up in terms of new storage technologies. We have significant labs and skills also here in France to test the technologies, to do performance assessment, aging assessment, cycling assessment, and all kinds of tests. And we are doing surveys, I would say, in terms of emerging technologies to be able to stay at the forefront of what's coming up. But when it comes to develop operational solutions like this, it was mostly a wise choice to leverage what's the most common technology on the market, which is again the lithium-ion battery that really works. The improvement again would be to use this second life EV battery. That's still a lithium-ion technology, but that was designed for a specific application, and that you turn into a new life, a new application during stationary storage. So that's an improvement. I really believe it's a good idea, but we'll have to prove it.
Sure. Thank you, Bruno, for the presentation. I think we'll have to stop in the interest of time, but look forward to some more work with EDF, and hopefully you guys do some more work in India.
Thank you very much.
Great. Jumping on to our next presentation, I'd like to invite Professor Ashish Garg over to sort of share his thoughts and insights from his work. Over to you, Professor Ashish.
Am I audible?
Yes, loud and clear.
Okay, thank you. So, thank you. Let me just, is my screen visible there?
Yes. Yes, your screen is visible. Ashish.
Great. Thank you. So thank you all organizers and Professor Jhunjhunwala for inviting me to deliver this lecture today. So I'll be basically talking about research challenges and directions which are there in silicon photovoltaics and also in perovskite photovoltaics, and how can we combine them together for further improvement. So I am associated with this newly created department at IIT Kanpur, Department of Sustainable Energy Engineering, which works in various areas of energy. We have more than 20 associated faculty members, and we are also recruiting faculty members, and especially in new and clean energy. So, and we also have recently started this Chandrakanta Keshwan Center for Energy Policy and Climate Solutions. So just a brief about the IIT Kanpur Solar PV Group's capabilities. We are engaged in research related to perovskite solar cells. We have been able to make single junction devices on materials which give us 20%, which are pretty comparable to world standard on those materials. And we have developed processes and materials which can provide us a stability up to 2,500 hours. And this is all being achieved using additive and microstructural engineering of materials. And we are also working on developing lead-free perovskite, given, as I'll show you later, that most of the perovskite materials have problems with presence of lead, which is not a very acceptable scenario. And also we are working to develop tandem solar cells, primarily based using perovskite and silicon or perovskite cells. We have also a strength in organic solar cells, and we have demonstrated already efficiencies of up to 12% on PTB7 based systems, which are again close to world standard. In these kind of devices also, we have demonstrated lifetimes of up to 2,000 hours. And we have had collaborations with industries like Mozarbayar and Tata Steel, and we have been able to develop large area mini modules up to 100 centimeters square area. For example, there's a picture here which shows you 8 by 8 centimeter mini module. We have capabilities in materials and device fabrications of all types. We can do advanced characterization, including lifetimes and so on and so forth, as well as impedance analysis and things like that. And we also have setups related to reliability testing. And all this, of course, would not be possible without the financial support from many funding agencies in India and overseas, as well as industries. And I would also like to thank my collaborators in India and overseas. So without boasting too much about my research, if you are interested, you can go to this website where you can look at the details of work that we've done. So coming to the context of this talk, solar PV is very important in Indian context. We have a potential of more than 750 gigawatts in this country. Current installed capacity of solar PV, as we all know, is about 40 gigawatts right now. And 2030 projection is about 300 gigawatts. And this is very much in sync with Prime Minister's announcement at COP26 that India will have 500 gigawatts installed capacity from renewables, which is indeed a very laudable target. And solar promise in India is very good, given that solar power tariff in India has fallen close to ₹3 per kilowatt hour. So if you look at solar, so I'll just go into brief basics of solar cells for those of you who don't know. So this is sort of the solar spectrum, which runs across, about 200 nanometers to 2,500 nanometers or so. And in this, the range, which is, you can say visible near infrared or maybe part of UV, these are the ranges which are utilized by the solar cells. So, a useful material to make a solar cell is a semiconductor, which has energy gap. And the ideal gap for a solar cell to operate at room temperature is about 1.4 electron volt. The commonly used material is silicon, which has a band gap of 1.1 electron volt. And this is optimized by the balance between current and voltage that we can get from the material. On the other hand, new kid on the block, perovskite, has a band gap which can be tunable between 1.3 to 2 electron volts. An important aspect of all these materials have to be that they have to absorb well. Any energy which is more than the band gap must be absorbed. but depending upon the type of the semiconductor, they have high or low absorption coefficient. So for example, if you look at silicon, which has a band gap of 1.1 electron volt, it can absorb up to about 1100 nanometers, but its absorption coefficient is lower. On the other hand, if you look at perovskite has higher band gap. As a result, it will absorb only up to about 900 nanometers, but it can give you higher absorption. So there is a trade-off between silicon and perovskite, but perovskite silicon numbers are close to each other right now. Another thing about the device is that charges, once you shine light, you create electron hole pair. The electron hole pair must be broken and it must be separated. And those free electrons and free holes must be transported to the electrodes for collection without any losses on the way, which means there should be no resistive losses, there should be no leakage, and there should be no recombination of charges, or at least minimum of losses. So the figure that we typically talk about solar cells is power conversion efficiency, which is nothing but output power divided by the incident power. So if you have 100 watt incident optical power on the solar cell, if you derive 10 watt, then your solar cell is 10% efficient. These are some very bare minimum basics of solar cells for those of you who don't know about it. So depending upon all these material considerations and processing improvements, solar technologies have evolved in this fashion. So generally, generation 1 technologies, which started developing after the discovery of p-n junction, are basically based on monosilicon, multisilicon, as well as gallium arsenide. These are typically wafer-based technologies where size of the thickness of the device is between 0.3 to 0.5 nanometer. On the other hand, if you look at generation 2 technologies, which were based primarily on thin films of cadmium telluride, CIGS, and amorphous silicon, all of them being inorganic compounds, there the material consumption went down from 0.3 to 0.5 millimeter to 2 to 5 microns. So you can see there is a 100 times reduction in the material used for a module. And coming to generation 3 technologies, which are based on dye-sensitized solar cells or organic solar cells or perovskite solar cells or multi-junction or tandem solar cells, the thickness of the device goes down to less than 1 micron. So we can see that material requirement has even gone down further. So all of this has tremendous potential for thin film solar cells because the material consumption is lower. However, because of many other considerations, silicon still remains the choice of technology. But there is a possibility that multi-junction, that generation 3 technologies can seriously occupy a certain amount of space for themselves. So out of these technologies, silicon is typically wafer-based, as I said, and generation 2 and generation 3 are thin film based. Generation 2 technologies can be processed using either physical vapor deposition or chemical vapor deposition processes, whereas generation 3 technologies are primarily solution process, which make them even more attractive to reduce the capex in manufacturing these solar cells. So not only they have lower material consumption, they also have lower capex for manufacturing, potentially speaking. But they have problems such as, because generation 3 technologies suffer from mainly the stability issues. Perovskites have higher efficiency, but they have lower stability in the ambient. So these are certain numbers about the efficiencies. So this is a chart which is updated by NREL in US almost every day. And picking up from this chart, if I enumerate some of the key technologies, then generation 1 monosilicon has, or crystalline silicon as we call it, it has efficiency, top efficiency of about 26.1%. Multi-silicon or polysilicon has 23.1%, whereas the silicon heterojunction technology has achieved 26.7%. So silicon altogether has achieved a peak of about 26.7 for a single junction cell. If you look at generation 2 technologies, among these, cadmium telluride and CIGS stand out, and both of them have efficiencies in the excess of 22%. And generation 3 technologies, organic solar cells, which are primarily based on polymeric materials, they have efficiencies exceeding 18%. On the other hand, if you look at perovskite, which has done remarkably well over a period of last 10 years, it has already achieved more than 25%. And perovskite silicon tandem, which has very bright future looking ahead, it is approaching 30% efficiency, which is actually which could be a game changer also for silicon, because silicon can adopt a new role into perovskite silicon tandem cells for certain niche applications, if not for every application. So this is sort of the maturity stage of various technologies. Silicon cells, both mono and polysilicon, they are commercialized. They are very much mature technology. Other variants of silicon such as TOPCon, PERT, these are these are about to be mature, but there is some work which remains to be done, especially from processing point of view. On the other hand, if you look at tandem technologies or perovskite technologies, these are still at the R&D stage, or to some extent they have been taken beyond R&D to sort of pilot line, but they have not been commercialized as yet. Right now, the market is dominated by silicon, combined crystalline silicon and multicrystalline silicon. More than 90% of solar cells worldwide are made of these two, and with a minor share occupied by cadmium telluride. Amorphous silicon is close to dead, whereas a very, very small fraction is occupied by CIGS. Looking ahead in 2050, the predictions are silicon will continue to dominate the market. In fact, the silicon fraction looking ahead in 2050 will be more than 95%, which doesn't bode well for other technologies, but we never know how technology, because I mean, we still have 30 more years to go. So research innovations and technological innovations can certainly make other technologies come on the surface. So first, I'll talk about the generation 3 solution processable solar cell, which is perovskite solar cell. It's a very simple device. What it has is it has a thin layer of absorber, which is made up of perovskite material, which is sandwiched between an electron transporting material and a hole transporting material, which are basically there to facilitate selective electron and hole transport to the cathode and anode. And this device is basically a solution processable device. It is very similar to organic solar cells in that respect. The substrate could be basically a transparent glass substrate. It could be either glass or plastic substrate. And the beauty about these devices is that these are solution processable devices. That is what makes them very exciting and promising. So if you look at perovskites, they are very close cousin of dye-sensitized solar cells. In fact, the dye-sensitized solar cell work in Europe led to the discovery of perovskite solar cells. So perovskite solar cells, the work started by Miyasaka et al. In 2009. They reported 3.8% efficiency on methyl ammonium lead iodide, but the cells were really, really unstable. They did not last for many seconds, in fact. In 2011, 6.5% efficient solar cells were made, which were stable for 10 minutes, but not beyond 10 minutes. The major landmark breakthrough came in 2012 from Oxford Henry Snaith's group, where they demonstrated 10.9%, again, methyl ammonium lead iodide chloride based solar cells, and reported this discovery in Science. Since then, this field has taken off. Today, perovskite solar cells stand at 25+%, and tandem based on perovskites stand at 29%. Perovskites, all of you may know, some of you may know that these are based on AbO3 structured material. So A is the bigger cation, B is the smaller cation, where oxygen makes an octahedra around this B cation. So if you look at the molecule of this, the molecule is CH3NH3Pb IBrCl3. So here the blue ones are A cations, the gray ones are B cations, and the purple ones are the anions. So there are a few compounds. It could be methyl ammonium based, it could be formamidinium or methyl ammonium mixture based, or purely Fa based. The choice of cation can also be tuned. It could be iodine, it could be bromine, it could be chlorine, or a mixture of these. The composition tuning in these compounds is very important because it can change the band gap, the optical properties, the microstructure, crystal structure, and so on and so forth. The device configuration is very simple because perovskite facilitates the ambipolar transport in the material. So you have a perovskite layer which is of the order of 0.5 micron thin. It is sandwiched between an N-type and P-type contact. The light falls on it. The electron hole pairs, they get separated very easily because the binding energy is very small, and they then get transported to the two electrodes. So there are a lot of good things about perovskites. They have high absorption coefficient, they have high diffusion length, they can be made by solution processing, they have tunable band gap, and so on and so forth. They are based on earth abundant elements. So these are all good things, which is what makes them exciting, but there are challenges. They are woefully poorly stable. The devices of most perovskites do not last few days. They have hysteresis issues in many of the devices, which means when you sweep IV curve in forward and backward direction, there is a difference. And most of the high performing devices, they contain lead, which is a clear no-no from environmental point of view. These three challenges make that road tough for perovskites, but at the same time, there are a lot of research challenges to improve these further. So a typical perovskite device consists of a transparent conducting electrode, which is either ITO or fluorinated tin oxide or AZO. The perovskite layer is either made of methyl ammonium lead iodide or formidinium lead iodide. Basically, the job of this layer to absorb the light and generate the carriers. The band gap is generally between 1 to 1.5 electron volt. However, the major challenge is the lead, which has to be replaced. Second important component is electron transport layer, which has to selectively transport the electrons to the cathode. And hence, we use typically materials like TiO2, tin oxide, or zinc oxide. One can also use organic materials like PCBM. The key requirement of this material is that it has to have low work function so that it can remove electrons, and then it must also have high transmittance in the UV vis region. And it is responsible for your exciton dissociation and electron extraction. At the same time, whole transporting material, which is also very important, generally made up of spirometad, which is an expensive material, moisture sensitive material, and that is why people are looking for alternatives in the form of oxides such as nickel oxide. And again, HCM material must have high hole mobility, and they should facilitate hole extraction and transportation. So the development of these three layers is at the heart of perovskite research, developing perovskite layer, developing ETLs, developing HTLs. And if you can get all three right, you are in for a high efficiency perovskite cell. But there are many issues, as I said, for perovskite cells. For example, they contain lead, which is an environmental hazard, which makes them unwanted, and that is why there's a lot of research that is being done on developing non-lead or reduced lead perovskite solar cells. They have a structural instability problem. The perovskite structure, the compound methyl ammonium lead iodide tends to degrade into other compounds, thereby leading to structural instabilities. And this is also affected very strongly by processing, how you process the device. Another important problem in perovskites is that they contain hysteresis in forward and backward. The picture here on the right shows you that when you take the IV characteristic, the reverse shows typically better characteristic as compared to forward. This is an issue in some of the devices. Most research groups report these hysteresis, and this is a combination of ionic charge migration, recombination, any other perovskite contact interfaces. The major problem with these materials is they have very poor lifetimes, and because they are very moisture sensitive, as a result, the perovskite compounds tend to degrade, leading to, for example, lead iodide formation. They have intrinsic stability issues. They also tend to degrade as a function of light. They also tend to degrade. They also tend to heat up when you apply voltages to them. And mechanical fragility is also an issue with these solar cells, especially in the flexible devices. So these performance-related issues make perovskite solar cells very apt for research, and there's a lot of learning which has to take place in this area. So, for example, one of the solutions to improve perovskite devices is to do strain engineering, which can control ion migration and improve the device performance. So, for example, in the view graph, you see that red ones show better performance as compared to the black ones, and this is because the red ones have higher compressive stresses in the films. One can also do interface engineering. So, for instance, the electron transport layer TiO2, if you put a little bit of chlorine in there, the chlorine tends to passivate these layers. As a result, the recombination is lower, and hence the device performance is better. It also tends to improve the hysteresis performance by reducing the ion migration. And one can add additives in the devices to control the grain size, and also to add to the passivation to improve the device performance. So, for instance, some of the work that we have done in our group is to develop, for instance, a tantalum doped TiO2, which leads to improved conductivity of TiO2, and it leads to improvement in the performance of the solar cells. We have also done some work on developing these TiO2. TiO2 is a notorious compound because of its processing temperature, which is quite high. It's about 500 degrees centigrade. So we have developed a process which is based on microwave engineering, whereby we have been able to reduce the annealing temperature as well as time. And we have been able to achieve 18% devices, nearly 4% improvement. So the control samples give about 15%, whereas microwave sample give about 18%. And these are good efficiencies for methyl ammonium lead iodide based solar cells. Another thing that we have done is we have developed the non-spiro based hole transporting materials, which are environment friendly, can be made easily, and these materials show efficiencies which are quite respectable as compared to control samples.
Some of the work that we have also done by additive engineering in perovskite solar cells. For instance, if you add PCBM to the PCBM is a fullerene, if you add fullerene to the perovskite in a very small quantity, it again leads to improvement in the performance as well as the stability. And this is basically because of passivation of the grain boundaries as well as increase in the grain size of perovskites. We have also done chlorine addition to the perovskites, and what we see is that chlorine addition leads to massive increase in the grain size. The grain size increases beyond 1 micron, and this leads to really efficient devices as well as very stable devices down to about 500 hours or so. So much of this work is related to additive engineering, compositional engineering, interface engineering. Other possibilities in perovskite solar cells to improve performance is, for example, chemical substitutions. You can replace the methyl ammonium by Fa or CS ions, which can lead to tuning of band gap. They can also improve the phase stability. And when you do all these things, this naturally leads to changes in the optical properties. One of the important aspects of A-side doping is that A-side doping also leads to enhanced moisture tolerance in the devices. So generally, A-side doping leads to more stable devices as compared to B-side doping. B-side is the lead side, so you can again replace lead with the tin, magnesium, iron, cobalt, many other ions, and this has effect on reducing the lead content. As a consequence, the toxicity goes down, and it also leads to changes in the band gap, which of course leads to change in the optical properties. And one can also change the halogen side by doping it with various ions, and they have again effect on the band gap, which leads to different color dyes. And they also affect the phase stability, conductivity, carrier diffusion lengths, as a consequence affect the device performance. So all of these doping on A, B, or X site lead to tremendous influence on electronic properties as well as optical properties of the devices and the microstructure as well. So sorry, how much time do I have?
So we're almost out of time. So request. Okay,
so I'll probably come to last slide or so. And one last slide I'll show you. An interesting direction in perovskites is to make 2D, 3D perovskites, where you mix 2D and 3D together, because 2D has better stability but poor performance. 3D has superior performance but poor stability. And if you mix them together, you can sort of obtain a sort of optimum stability and performance combination in these cells. And this is sort of some of the plots which are taken from literature, where it is shown clearly that 2D, 3D solar cells can have better performance as well as stability. Can have better stability but not performance as compared to 3D solar cells. I'll briefly go to silicon solar cells. In silicon solar cells, we have right now the standard architecture uses aluminum back surface field silicon solar cell. The problem in these solar cells is because of heat, because you have the back surface which is not well passivated and some of the light is absorbed by aluminum. There's a bit of heating as well as loss of efficiency. So these are about 20% efficient. The improvement in silicon is given by this PERC, which is passive emitter rear contact device. And if you do the passivation on the back side as well as on the front side, this is a passivation and recombination is the major issue in silicon solar cells, which is tackled by most researchers, and this is what leads to improved performance. The other technologies which can lead to improved performance as the TOPCon design or interdigital back contact design or silicon heterojunction, they all have led to efficiencies which are more than 25%. So silicon, looking down the road, probably silicon is going to be replaced by PERC technology in the years to come, with some fraction going to be occupied by silicon heterojunction. Silicon is again not a dead technology. There are quite a few issues which can be taken up by researchers, such as to improve the contacts, to minimize the recombination, as well as to improve the new device such as TOPCon and silicon heterojunction. So the new way forward for silicon and perovskite both is developing a sort of tandem solar cell. So if you can make a tandem device where if you have a single junction device, for example, silicon, you can only absorb from 800 to 1200 nanometer. If you combine a wide bandgap perovskite with silicon, you can absorb large amount of light, thereby giving you higher efficiencies. And this is where silicon tandem are very attractive. And I will probably close at this point that silicon tandem is probably a future technology to look forward to, especially in the market which is dominated by silicon. So with this, I'll stop here. Thank you very much. If you have any questions, I'll be happy to answer.
Great. Thank you so much, Professor Ashish. We'll have just time for one question if anyone has, but in the interest of time, I think we should be moving on.
Okay. Yeah, we are already 45 minutes behind, getting late.
Thank
so
you.
I suggest that we go to the next topic.
Thank you, Professor Ashish again.
Thank you very much. Thank you.
Please stick to time. Please.
For the next presentation, I'd like to invite Dr. Hiranmayi Vedam. She's an IIT alumnus. Yep. Over to you, Hiranmayi, if you're ready, and request you to please keep it within the 15-minute time slot. If you could wrap up in 12 minutes, we can also have some time for questions.
Okay, thank you, Professor Janimala, for inviting me to speak here. So today I will be talking about what are some of the opportunities and gaps in commercializing sustainable energy technologies, especially in the context of India. So all of us are familiar with how technology goes from lab to market. So we have principal stage, which is mainly happens in the lab, and then proof of concept, proof of value, and so on. And many times it's not a linear process. There is an iterative process that happens where we have to keep going back and forth. So this research phase, the first phase of research, is mostly invisible to more the investors or the customers. Development phase, which is a very important part of commercializing many of the newer technologies that we've been talking about yesterday and today. And then we have the productization, market expansion, and growth. So this experimental development phase of proof of concept and proof of value may not be needed at all times, but it's specifically needed when there is
your connection is not good.
Around the commercial parameters. 6 months or two. Hello.
I think your connection is not good. We are not able to hear you properly.
Do you want to switch off your video?
You have to switch off your video and try that. Yeah, go ahead.
Okay.
Yeah, better.
Is this better now? Okay. So we need to do the experimental validation stage when there is significant uncertainty around the commercial parameters and the time it takes to determine the commercial parameters. And of course, the third factor is if it's going to cost us a lot to get some certainty around commercial parameters and time, then it's very difficult to get either customers or investors to chip in. So that's where we have to find other sources of funding and other ways to validate the technology before you can go to the market with a product, minimum viable product and so on. And again, because of this, most technologies fall into this valley of death, somewhere between the proof of concept to product market fit stage. A determinant factor in improving these outcomes is the quality of the ecosystem we are in. So that involves the research, innovation, and entrepreneurial cluster, and also the macro environment we are in. So if the research cluster, of course, includes the institutions, the academic institutions, the research institutions, the space and equipment kind of things that are available to them. The innovation cluster is where most of the gaps exist in the Indian ecosystem, where translation, technology transfer, finding the right skills and space and equipment, all of these become a challenge in the Indian ecosystem. Then we have the entrepreneurial ecosystem. India has a very well-developed entrepreneurial ecosystem, but has a lot of constraints as far as sustainable energy and climate tech-related innovations are concerned. So even though we may have these three clusters in some pieces or the other, the thing that determines the flow of ideas from research all the way to market and our ability to commercialize them is based on the macro environment. which includes the government policies, the regulation framework around these newer technologies, the financial infrastructure, the legal infrastructure, and so on. So if we look at the sustainable energy space and look at where investments are happening, especially, we went through one, hype cycle and collapse way back in 2008, 9, and so on. And now we are entering another cycle of increased investment into this space. And technology between the 2010-11 and now, many of these technologies have matured quite a bit, and the technology risk has been substantially reduced for many of them. And there are specialized clean tech investors who are willing to take those long-term bets like breakthrough ventures or Renault. And even generalists are starting to invest in clean tech. Okay, corporate investment funds are specifically focusing on sustainable energy technologies. And generally, everybody agrees that you need to have a long-term view in order to be able to take these technologies to the market. And that realization has evolved new venture capital models or investment models into clean tech. However, if you look at where the money is actually going, we see that most of the new investments are going into later stage technologies, which means product market fit or even business model fit or growth stage. So that's where most of the money is going in this space. And whatever we call early stage, the money is going into digital or software opportunities and not into the kind of things we've been talking over the last few days. And the investments are more focused on technologies or solutions that are synergistic with existing markets or existing technologies rather than disruptive or breakthrough innovations. So we can be cautiously optimistic, but we are very far from being able to commercialize the breakthrough technologies we are seeing today. If we look at the Indian scenario, only one company in India made it to the Global Clean Tech 100. Okay, and very few investors are investing in the pre-seed or Series A stage in energy. And if you look at the number of transactions in the clean tech space is coming in. Even in this frothy space that we are seeing, the frothy investment market we are seeing, very little is going into clean tech or sustainable technologies. This analysis that was done in 2017 indicates that India is still below average on most metrics related to global innovation in the clean tech space, except for the clean tech specific innovation drivers. And that's because we are investing a lot in the PE stage or in the much later stages because India inherently is a very large market for energy. Okay, these two pictures again show a similar story of very little money going into clean tech and mostly into solutions and very little into equipment or any other areas. But not all, we realize this inherently, but not all clean tech startups are equal. Many of the technologies we talked about today, materials related, hardware related, are very hard to commercialize. And whereas the software, finance and other clean tech opportunities are easier to, convince an investor because of the returns that people are seeing in those fields. Okay, but if we look at where we need real innovation to reduce costs or to improve the efficiency or any of these parameters, commercial parameters, most of it needs to happen in the material space. So whether it's batteries, whether it's solar cells or wind, the materials need to be improved. And any material technology takes anywhere between 10 to 15 years before it hits the market and it can be commercialized successfully. So therein lies our dilemma in terms of how do we make these how do we get these newer technologies to the market faster, and what can we do about it? Okay, and not only that, in the clean tech space, we don't have a single valley of death. In fact, we have multiple valleys of death, because there is one that is associated with the technology, one related to scale up, and one related to deployment, because deployment needs to be integrated with existing energy infrastructure. Scale up means that you have to scale up the manufacturing. So there is the technology scale up, there is the manufacturing scale up that needs to happen. And then the deployment, because of the integration, because of the energy systems that we already have in this world. If you look at the funding available to startups in India, there are many funding schemes that are available, but very few of these are really applicable to clean tech or sustainable energy related spaces. As it is for all sectors, the early stage to expansion phase, which means the product market fit to the pre-product market fit stage to business model fit stage, is a very hard one in India. It is even harder for clean tech, because the amount of funding required for establishing proof of concept or proof of value is very high, and the ticket sizes of typical funding from these grants is very small. So if you look at the research ecosystem in India, we have a well-developed research ecosystem, especially in the top tier institutes. But most of the focus when doing research is based on novelty of the technology and how new is it compared to whatever else is there in the published literature. We need to combine it with a thorough understanding of the industry value chains, and where the new technologies can add most value. And also try to understand the ecosystem, our own ecosystem, and the ecosystem for growing or nurturing that technology all the way to the market, and what are the gaps in that ecosystem. So by having that sensitivity, or by adding that sensitivity in selecting the research topics, we could increase the commercialization ability. In the innovation ecosystem, as I mentioned, there are a number of gaps in the Indian ecosystem. There is very little explicit funding available for translation. So mostly this is funded by researchers through their own consulting projects, or these project staff are put on other projects. The space and infrastructure for doing these kind of translational work is also very limited, because you're not talking about something that you can do in your research lab. You need larger space, you need specialized infrastructure, and those are not readily available. And IP support services in most academic institutions today does not go beyond administrative support. And the technologies aren't packaged well, and the IP support staff don't have the maturity to make decisions about IP protection or commercialization terms or the implications of these terms. Similarly, if you look at the startup teams that are forming, most of them are comprised of students or project staff. And it's very rare that you see an experienced professional being added to the team in the innovation phase, the translational phase. And these people are important to be able to provide that industry connect, that industry knowledge, and so on. And there is also limited mentoring available in this phase of the commercialization, because most of the mentors are executives or retired executives who have a lot of business experience and who can help with the later parts of the commercialization journey. But the technology transfer part or the translational part is a techno-commercial legal kind of space, and that's where the mentoring is weak in the Indian ecosystem. And industry connection is also very limited, primarily because industry in India looks for more mature technologies before they can adopt it. And this gap needs to be, the engagement with the industry during the translational phase is very hard. Okay, and there is also limited absorption capacity in the Indian industry for these kind of strategic partnerships or co-development kind of areas.
Please wind up now.
Yeah, I'm almost done. So in the entrepreneurial ecosystem, we have, as I said, we have a very strong entrepreneurial ecosystem, but mainly focused on the B2C, business model innovation, financial model innovation, services, SaaS, software. These are the things that the entrepreneurial ecosystem understands very well. There is limited understanding in the electronics and mechanical hardware space, but that's more than in some other things. And they're also very familiar with India-centric business models. But if you take a startup with IP as an asset, this is an area where very few investors understand this. And if there are, you combine it with regulatory uncertainty or network effects, then it becomes very challenging for the investors. And similarly, B2B is a space that's very hard. Materials or process-based startups find it very hard because of that lack of understanding. And if you go into like global business models, the Indian investors find it hard to go with it. All right, so in order to address this, what at least the innovation ecosystem and providing some training support, I've created a YouTube channel where I have kind of created short videos on many of the topics related to this translation and some of the things that the researchers need to look for in commercializing these advanced technologies. I also created templates for the early stage, identifying the right idea that can be commercializable. And one of senior IIT Madras alum, Rajesh Shrikant, and we developed a mentoring framework so that the mentors can use it to help the entrepreneurs along their commercialization journey better. There is also a mentoring guide that has the detailed questions that go with that mentoring framework. And right now we are trying to simplify it and come up with some metrics so that it's easier to assess where the startups are or where the technologies are. And we can guide, the mentors can guide them towards successful commercialization effectively. Thank you. That's about all I have.
Thank you.
Thank you.
Thank you very much. And in the interest of time, I think we'll go to the last talk of the day. Professor Sagar Mitra. He's supposed to be the guru of lithium-ion battery technology, trained generations of people, and now, so we'll request Professor Sagar Mitra to give the concluding talk.
Thank you, sir. I'm sharing my slide. Hello, good evening, everyone. So first of all, thank you, Professor Junjunwala, for your invitation. And today I'm in Delhi. I'm talking from the hotel. Okay, so I'll be talking about sustainable energy. That's our theme. And what I feel from the angle of storage as well as solar fuel, I'll discuss about it. Many people may not agree, but it's fine. But that is my way of looking at it. I'm from Department of Energy Science and Engineering, IIT Bombay. So if you look at what are the greatest challenge right now, 21st century, I think we need to go for a low carbon energy. We need to go for, we are facing climate change. Also, we need to think about how to get a sustainability, whatever you use, how to make it sustainable. So if you look at world population is increasing, so that's a reason all the whatever we are discussing here, I think throughout the presentation, we'll be seeing all the things what I am discussing, it is already discussed. And at the same time, we'll be reducing the emission problem need to be reduced. So this is a very challenging problem, and everywhere in the world is looking for the solutions. So if you look at what are the things could be, we are thinking about net zero emission in the world. It is very nice to see in the net zero emission in the pen and paper, but it's a very difficult to make it that. And several reports, even I was looking at several reports, what they're talking about net zero emissions. And it was some way the conclusion of every papers or every literature says that there will be significant demand, even though if you go next 50 years, there will be some hydrocarbon fuels will be persist still if you are thinking about net zero situation. I'll come up of this, why I am telling this, hydrocarbon fuels will be still there, some of the percentage. Okay, so next is, if we are using, let's say we are achieved some nearby net zero conditions and we are using some hydrocarbons for some particular purpose, we know we cannot avoid that hydrocarbons for that type of purpose. In that case, we need to capture carbon dioxide. So obviously there should be a solution for carbon dioxide capture should be captured. And another thing is you need to think about bioenergy to negative emission offsets. So that is another thing should be thought. You should think about how to have a technological solutions, because using bioenergy is very old technology. I don't think our country is also very good on this bioenergy uses. But we need to think how to improve the technology so that we can offset some of the negative emissions. Okay, so since I'm a lithium-ion battery researcher or battery researcher, so I will always talk about transport or any other solar renewable energy storage as the options. In that sense, emission, if you look at the sector-wise where the major emissions comes, two sectors, one is electricity production, another is industry, and third is from the transport. So it's a major things. Another one is agriculture. We don't have much solutions for this right now because we don't know what are the problem comes from the agricultural sector where you should have a solutions. So we'll be talking about, I think throughout these 2 days or 3 days, we'll be talking, we are talking about this transport sector, how to minimize the emissions. And if you look at it right now, worldwide, even India is looking for large scale electrifications through significant of solar PV and wind. So that is even India also going in that directions. Industrial sector also looking at greenhouse emissions are, but some of the industrial sector like cement industry, steel industry, from the process line, emission factor is very difficult to reduce, but they're trying. So they are also trying to reduce that. But that is a major factor right now in industrial sector. You think about decarbonization of heavy duty transport. We may not have much solution right now. That ships actually makes a lot of emissions due to the ship, and they are all operating on the diesel. And aeroplanes, we are not even looking at, this is the one I feel is the less efficient compared to any transport we use. Even the bigger lorries, even truck, that need to be look at it then. And right now we may not have much solutions to decarbonize this type of heavy duty vehicles. And if you look at another one, which is 50% of total energy demand, which is coming from chemical industry as well as material industry, which is coming up very much like a chemical industry and material industry because of a lot of innovations is going on in materials and chemicals. These two industries actually growing up like anything. So 15% of total energy demand is actually coming from these two industries. We should think about how to have a solution out of it. So we don't have much solution right now. And I'll be talking about EV. So that's my domain of research. So there's a few myths of EVs. Carbon dioxide emitted from the power generation makes a green option. EV cannot, if EV is, the battery of EV is charged from the regular power supply, we are not having a we don't actually solve much on carbon dioxide emissions. So we need to think about renewable integration on the battery charging system. And that is, I think, is worldwide is going on that. And in our country, we don't have much power supply which can be utilized for electric vehicles. We need to think about it because this will be extra burden for the grid levels. And we have another good things is the tropical climate, and most of the technology coming from battery, coming from BMS, coming from thermal management is only designed for some of the European countries as well as in US, United States. But we don't have much solutions or need to improve the solution, improve this technology so that it can sustain on tropical climate. So this is another challenge we have right now. Again, the last option is oil import, lithium, cobalt imports. We always talk about these two imports. I always add another import for the industry, for India, it is a technology imports, because we don't have much technology. Much people are working on this type of technology so that industry can take it up and do it. So we need to, again, think about technology imports for the country. Okay, so I was talking about there is a always says that you need to have a electric vehicles, battery should be charged from renewable energy. You can mix up the renewables, like a mixed renewables, can be solar, hybrid. There is the best option is, let's say, hydrothermal and solar can be hybridized so that get a better efficiency in the battery storage system. And if you look at the battery, we always blame the battery technology is not much increase. Obviously, I have given an option, I have given a written in the red line, so that you can see we started with lead acid battery, which is 30 kilowatt hour per kg. Right now we are 220, so around 3 to 4 to 5 times of increase of energy density happen in 200 years. And right now we are looking at 220 to 300, 350, even 400 watt per kg of energy density. And we need to always think about this is possible another 5 years or 10 years or not. Maybe possible, but we need to think about it because past history doesn't show that, because 200 years was used to increase 5 times. So we cannot have another 2-3 times of energy density increase within very short time. And unless until we are your electric vehicles batteries are not charged from renewables, we are not solving much carbon dioxide emission problems. And there is another scenario for India. I was doing this. So if you look at it, I has mapped our solar photovoltaic installations, the major places, which is Rajasthan and Gujarat. And if you look at, I have given the monthly temperature variation from the maximum to minimum. You can see huge temperature variation where the maximum solar storage is there. And if you look at the solar, this temperature variation, so which chemistry or which battery storage can be applicable for this type of renewables, I think that is a question. Even I was trying to fit our best lithium-ion battery, which operates nicely with 20 degree to 42 degrees centigrade temperature without much thermal management system. It is very difficult for this type of fluctuation. So what is the problem? If you do this type of storage, this type of location, you will be reducing your lifetime. So that's a problem. And if you try to introduce some kind of cooling system, people say air conditioning room and putting the battery, that may not be the solution for large scale storage options. So we need to think about it, what type of chemistry can be applicable for where the largest solar deployment. So which type of vehicles India should look at it? Even worldwide, couple of sizes of vehicles people are looking at it. I'm talking about 2 types of vehicle. One is very small and the battery use is 40 kilowatt, 24 kilowatt hour. Other is very large, which is Tesla model, which uses 90 kilowatt hour battery size. If you look at the battery size, I don't think lithium reserve doesn't have a problem. Right now, this is oil known. Lithium reserve may not be a problem because recycling already there. Recycling technology is already there, also recycling. Lithium problem may not be that. The problem, as per my opinion, problem is the weight of the batteries. You see that if you take the Tesla car, which uses 90 kilowatt hour of batteries, the vehicle weight and the battery weight is just 25% of the battery weight is the weight of the total car. So that's a huge problem. So we need to work on the energy density right now, volumetric as well as energy is gravimetric. These two are very important right now to improve the car efficiency. Even Tesla car is very efficient without battery, but when you put a battery with the let's say 500 kgs of batteries, cars are getting less efficient. This is another thing we should look at it. why I'm talking about this, India should look at the smaller car. Why the size of battery is small, uses of lithium cobalt will be small. Another thing is, I was doing a calculations. So different range, like all of the city where the electric vehicle will be used, maximum 200 kilometer per charge can be taken up. In that sense, if I do what is the battery weight, what is the battery cost with the two scenario, 180 and 125, very low cost to the higher cost batteries. And if you compare with the petrol cost, we are having a huge saving with electric cars. If you are only using a small battery, small car, like a 160 kilometer range, if you are doing it, you are saving huge. You can see $3.5 per kilowatt hour compared to the $20 per kilowatt hour in the IC engine, compare that. But if you go in a larger distance in the one battery charge, then your prices are increasing. That is also true for the other vehicle, other IC engine also. So in that sense, what I feel, unless until we have a huge tangential change on the battery technology or car technology or motor technology, I don't think much change will be there. In the battery technology, obviously there will be change, but not much. In that sense, maybe we should think about considering a small car. I think India is looking at the small car and the small battery so that everything is balanced way. So this is one way. Other things I was trying to do, if the battery used for aviation, because aviation is another one which is actually more polluted more than any road transport. So if you look at the, just take a simple drone. Drone during the takeoff and the landing, they use more maximum power, and there is energy density is important, also power density is also important. Similar thing is for the flight also. So if I take a very small example of drone, there are two operations are very highly powered operations. Other than that, distance is only depends on how much energy, how much battery size you are using it. So these two are very different from the electric vehicles. Electric vehicles may not be that much critical, but drone is very critical in that two sense. But in that sense, can I make a battery with a known chemistry with the same energy density but more power? Let's say a 5C and 10C for certain time, let's say a few minutes of time. Is possible. Some of the like a battery I have listed here, some of the chemistries can be combined, and oil engineered product can go to this place where we need to have higher energy density and good, like a 5C rate. It is possible. So people are doing it. So why not? We can also do. Next question comes: can I use for vehicles like aeroplanes? Yeah, if I see the black line what I have given, this black line is for the limitation of the batteries. So after that, is very difficult for any electrochemical storage right now with the power and the energy density. And all the graphs was given there, all the three color graphs are different type of vehicles, like air vehicles. And I think that is a limitation of the electrochemical storage, which may not be suitable for air travel, so air aeroplane things. But other accessories can be powered by the electrochemical storage, but not the fueling of the vehicles. This is one thing is right now is sure. Okay, so next is what are the chemistry people should work in India when you see it in India? I feel this is the chemistry, so the combination should we look at it. Sodium, sulfur, then manganese as a cathode material, and sulfur should be cathode materials. This is the chemistry. If you can look around and work on around this, you can get a very good energy density as well as power density, and easily available in our country. Even titanium also there. So I think whoever is working in this field, they should work on these 2, 3, 4 elements or 5 elements. Carbon is always there. So these few elements can be added and add the capacity, safety, and sustainability so that we can actually sustain. We should not look at our raw material supply from outside and then make the technology. So there is a transition right now. People are talking about lithium to sodium transitions because they share the same technology, and we know that almost same classic structure of electrodes are used for both cases. And people talk about cost. I'll give you one example where the cost is only the changing, which is on the salt. So if you compare the lithium iron phosphate and sodium hexafluorophosphate, lithium hexafluorophosphate and sodium hexafluorophosphate, these two having huge difference in the price. So whatever you are making the electrolyte cost, only the cost will be reducing. Other than that, nothing, no change will be there. A major change on the lithium and sodium and battery. So whoever is talking sodium will be cheaper is not. So this cost on the salt is that also counted now. 3 to 4% reduction on the price per kilowatt hour will be there if both having the similar kind of performance. So there is always question power density, energy density, cycle life of sodium-ion batteries. Some of the battery people are like some companies, startup companies are saying, but it's not proven because we don't get any battery yet. They are talking about energy density is quite good, like a 150, which is very much comparable with your LFP batteries. And they are talking about 10C in the pouch level, but it's very hard to believe. But it may be possible, but you need to see how much cycle it goes, because once you use the hard carbon, that is anyway work as a capacitor. But there is several engineering factors are there where you can reduce the timeline, like a C rate. And another interesting plot which shows that compatibility of any energy storage. I have listed all the energy storage and their compatibility in different sectors, like say specific energy, specific cost, power grid compatibility, operating temperature, and fast charging capability. If you see only one, you should see, which is talking about hydrogen. Most of the scale hydrogen is highly compatible, okay, compared to any other electrochemical system, and that's the reason maybe people are talking about much. But one should think about the hydrogen having a past history. We look at it, hydrogen is not much encouraging as a researcher. I don't know, people are talking about much. Even today also several people are talking about hydrogen, but I don't feel much thing, because last decade has not given me not enough confidence of hydrogen. Very slow progress anyway. And I feel this is a very region and problem, because hydrogen needs a completely different infrastructure if you compare with the battery storage, like a battery charging system. Hydrogen infrastructure is completely different and is costly. I don't know we can make that many infrastructure very short time. That's another thing. Several scenario, even Shell company like Shell is giving a scenario that hydrocarbon based may not be the zero uses. There will be uses because of several reasons are there. Okay, you should look at their reports. And another thing is, with the society, the more challenges will come when you have to have a carbon neutral. So our society may not be ready yet, and you need to give more and more talks, and even educate them how to make it more carbon neutral in the society. Okay, so this is a very good paper. If you are interested, please look at it. They have given two scenarios in next 50 years where the things will go. Right now, fossil fuel is the major like energy productions, and next 50 years they're predicting this can go. There'll be fossil fuels, there'll be renewable energy, but bio also included on this. And our country having a huge bio resources, we should also look at it. Another scenario is given, which may not be the good one, like a 100% renewable with the solar fuels, like a hydrogen or any other solar fuels can be looked at it. But this scenario is still under questions. But maybe likely this scenario will be the one who will be coming. Okay, so since we are talking about solar and storage, we have a center in IIT Bombay, which is funded by Ministry of New and Renewable Energy Sources for last 10 years. And huge funding. We have established our facility to make silicon solar cells, and we can have a research on silicon solar cell. We are working right now 22 efficiency of silicon solar cells and cost-effective solution for inverters. I am also working on the storage for the stationary storage as well as the electric vehicles and perovskites. What Professor Garg was talking about, perovskite solar cells. You have a very nice team on perovskite solar cells. Also, major things as IIT, we always train manpower for renewable development as well as for the battery development. So that's a manpower we develop. Thank you very much. I have finished my talk. Thank you. If you have any questions, please write
Thank you very much. Is there one quick question? Someone has? We are way out of time. Sorry, Professor Sagar Mitra. It was our mistake to put you in the end.
No, it's okay. Thank you, sir. So because I was in a meeting, so that is good that we have put in the last. So if any questions, anything you can write in the chat box. Otherwise, you can ask directly. Otherwise, we close. Yeah.
I think we will wind up now. Thank you. I think it was late.
Already late. Yeah.
Okay. Just want to say a quick thank you to all our presenters for today, for joining us, sharing with us your insights and learnings. And with that, we'll close our session today. Thank you all for attending.
Thank you. Thank you very much.
All the very best for all your work. One small request for all the speakers to please share with us your presentations. You can send it to me, Anson. I will share my email at the chat box.
So can you do it now?
Yes, I'll just do that right now. I've just shared my email on the chat box. Please do share it with me whenever you get a chance. But thank you all again for joining us. And if anyone's visiting Chennai, you're always most welcome to the IIT Madras Research Park. We'd love to host you and take you for a tour here. Thank you all, and please reach out if you have any questions.
So you can close down. Thank you.
Sure, sir. Thank you.
Thank you.